find a comfortable position wherever you are right now. Let your shoulders drop. Let your hands rest somewhere soft. Let the weight of the day begin to settle downward, out of your chest, out of your thoughts, down through the surface beneath you and away. There is nothing you need to do in this moment. There is nowhere you need to be. There is only this, the quiet, the darkness behind your eyes, and the gentle sound of a voice that wants to take you somewhere extraordinary before you sleep. Imagine, if you will, that you are lying on your back outside. The ground beneath you is firm and cool, the kind of coolness that seeps through fabric slowly and makes you feel anchored, held by the earth itself. The air around you is still, not cold enough to be uncomfortable, not warm enough to be restless, just still, the way air gets in the deep middle of the night when the world has finally stopped moving. Above you, the sky is open and enormous, and the stars are out. Not just a few stars, not the washed-out handful you might see from a city window, but thousands of them, scattered across the darkness in every direction, each one a point of light so steady and small that it seems almost impossible that something so faint could have traveled so far just to reach you. You are lying there, breathing slowly, and the stars are above you, and for a moment you do not think about anything at all. You simply look. This is where we begin tonight. Not with equations, not with diagrams, not with the careful language of textbooks, but with this, a person lying beneath the stars, looking up, feeling the particular kind of smallness that the night sky has always given to human beings. It is a good smallness, not the kind that frightens, but the kind that releases. The kind that reminds you that your worries, as real as they are, exist inside a world that is itself inside a solar system, that is itself inside a galaxy, that is itself inside something so vast that even the word vast feels inadequate. And tonight, we are going to follow that thread of inadequacy all the way to its most extraordinary end. We are going to travel to the very edge of what light can show us. We are going to find something there that should not exist, something enormous and cold and strange, sitting in the oldest light in the universe like a wound that has never quite healed. And then we are going to sit with the most astonishing possibility that modern science has ever seriously entertained, the idea that the mark we find there might be a bruise, the kind of bruise you get when something bumps into you, and that the something that bumped into us might have been another universe entirely. But we are not rushing there. We are not in a hurry. The night is long and the sky is patient, and the cold spot in the ancient light has been waiting for billions of years already. It can wait a little longer while we find our way to it gently. So stay where you are. Keep your breathing slow. Let the imaginary ground beneath you hold your weight. Let the imaginary stars above you do what stars have always done for people lying awake at night wondering about things too large to fully understand. They shine, quietly, steadily, across distances so immense that the numbers lose their meaning. They shine. And each one of those tiny lights is not just a light, but a story, a piece of history, a message sent from another time arriving here, arriving now, arriving just for you. Think about that for a moment. When you look at a star, you are not seeing it as it is right now. You are seeing it as it was when the light you are now receiving first left its surface. For the nearest stars, that might be just a few years ago. For others, it might be hundreds of years. For the faintest, oldest light we can detect with our most powerful instruments, the light has been traveling for nearly 14 billion years. 14 billion years. The universe itself is only about 13.8 billion years old, which means some of the light we can see left its source very shortly after everything began. That is the idea we are going to follow tonight. The idea of the oldest light, the first light, the light that carries within it the memory of the universe's earliest moments. And hidden inside that ancient, beautiful light, there is something waiting, something cold, something vast. something that has been puzzling and unsettling and electrifying the people who study it for decades. But first, we simply lie here beneath the stars, breathing, feeling the night around us, letting our minds relax into the enormous gentle darkness. There is a kind of peace in looking upward, something about the vertical direction, something about tilting your head back and letting your gaze extend outward into depth rather than scanning a flat horizontal surface full of objects and tasks and things that need to be dealt with. When you look up at the night sky, your visual field becomes depth itself, becomes distance, becomes time, and something in the body responds to that by letting go. Let go now. Let the stars hold your attention lightly, not with the grip of focus, but with the soft pull of wonder. You do not need to understand them to be comforted by them. You do not need to know their names, or their distances, or their temperatures. You only need to let them be there, above you, steady and ancient and indifferent to all the small urgencies of your day. The night is quiet, the stars are out, and somewhere in the oldest light that exists, in a part of the sky in the direction of a constellation called Eridanus, there is something waiting to be understood. We will get there together, slowly, one breath at a time. For now, simply rest, and let the night begin to work its quiet magic on whatever tension is still holding itself somewhere in your body. The story we are about to tell is one of the most astonishing in all of science. Not because it is full of action or conflict or drama, though in its own way it contains all of those things, but because it asks a question so large and so strange that simply hearing it properly is enough to make the ordinary world feel different. The question is this: what if our universe is not alone? What if it has neighbors? And what if one of them, billions of years ago, in the very first moments of what we experience as existence, brushed against us and left a mark? That mark, if it exists, would be the most important discovery in human history. It would mean that everything we have ever known, every galaxy, every star, every atom, every thought, every moment of love and loss and wonder, exists inside one bubble in a vast and perhaps infinite sea of other bubbles, each one a universe of its own. But we are getting ahead of ourselves. The stars are above you. The night is quiet. Breathe. We begin at the beginning. There is something extraordinary that happens every time you open your eyes. You are not seeing the world as it is. You are seeing the world as it was, a tiny fraction of a moment ago, the precise amount of time it took for light to travel from whatever you are looking at to the surface of your eye. For most practical purposes, that delay is so small it is meaningless. Light moves so quickly across the distances of everyday life that the lag is impossible to perceive. But it is real. It is always real. And when we extend this simple fact out to the scale of the cosmos, it becomes not just a curiosity, but the most powerful tool we have for understanding the history of everything. Light remembers. That is the heart of what we need to understand as we begin this journey. Every photon, every tiny particle of light, carries within it information about the place and moment it was born. When light leaves a source, it carries the signature of that source with it, encoded in its color, its energy, its behavior. And it carries something else too, something even more remarkable. It carries time. When you look at the moon, you are seeing the moon as it was about 1.25 seconds ago. That is how long it took for light to cross the distance between the moon and your eye. When you look at the sun, you are seeing it as it was 8 minutes ago. The sun you see right now, the bright disk that crosses the sky each day, is already 8 minutes in the past by the time it reaches you. The sun as it exists at this exact moment is invisible to you because its light has not arrived yet. It is on its way. When you look at the nearest star beyond our sun, a small dim red star called Proxima Centauri, you are seeing it as it was more than 4 years ago. For years of travel time, across a distance so large that if you were to drive it at the speed of a car on a motorway, it would take you about 40 million years. And Proxima Centauri is our nearest neighbor. Most of the stars you can see with the naked eye are much farther away than that. Some of the stars you see on a clear night sent their light toward you hundreds or even thousands of years before you were born. Think about what that means. Some of those stars no longer exist. They may have exploded or faded or been consumed long ago, and yet their light is still traveling, still arriving, still being seen. When you look at the night sky, you are looking at a graveyard and a nursery simultaneously, stars that are gone, stars that are being born, stars in every stage of their existence, all of them showing you not their present but their past. The night sky is the largest time machine ever built, and it requires no technology to use. You only need to look up. This relationship between light and time is not merely poetic. It is the foundation of everything we know about the universe beyond the reach of human exploration. We cannot travel to other galaxies. We cannot send probes to the farthest reaches of space in any time frame that matters to our civilization. But we can look. We can collect light. We can analyze it, measure it, decode it, and from that ancient traveling information, reconstruct the history of everything. The further out we look, the further back in time we see. This is both the great gift and the great limitation of astronomy. The gift is that the universe has preserved its own history in light, and that history is still arriving. The limitation is that we can never see things as they truly are right now, only as they were when their light departed. For nearby things, that lag is trivial. For distant things, it becomes enormous. And for the most distant things of all, the things at the very edge of what we can observe, the lag is almost as old as time itself. There is a horizon to how far we can see. Not because space ends there, but because light ends there, or rather, because the light that could come from beyond that horizon has not had enough time to reach us yet. The universe is about 13.8 billion years old. Light travels at a fixed speed. Therefore, the most distant light that could possibly have reached us is the light that has been traveling for approximately 13.8 billion years. Beyond that, there is more universe, perhaps infinite amounts of it, but its light has not arrived. We are, in a sense, waiting for it. But here is something even more astonishing. We cannot see all the way back to the beginning. Not because the universe was empty before a certain point, but because the universe was once so hot and so dense that light could not travel freely through it. In the very earliest moments after the Big Bang, the universe was a seething, brilliant plasma, so full of charged particles that photons, the particles of light, could not move more than a tiny distance before being absorbed and re-emitted. The universe was opaque, not dark, not empty, but opaque, like the inside of a star, full of light that could not escape, that could not travel, that could only bounce and scatter endlessly. For hundreds of thousands of years, this was the state of the universe. Brilliant, hot, dense, and opaque, a fog of light that could not move. And then something changed. The universe had been expanding since its beginning, and that expansion cooled it. As the temperature dropped, and as the particles that made up that early plasma began to slow down and settle into new arrangements, something happened that astronomers call recombination. The electrons and protons in that ancient fog found each other. They joined together to form neutral atoms, hydrogen atoms mostly, simple and stable. And when they did, the fog cleared. Suddenly, for the first time in the history of the universe, light could travel freely. The photons that had been trapped, bouncing and scattering endlessly through the brilliant fog, were released. They streamed outward in every direction into the newly transparent cosmos, and they have been traveling ever since. That release of light, that first moment when the universe became transparent, happened approximately 380,000 years after the Big Bang. In cosmic terms, that is extraordinarily early, a blink of an eye against 13.8 billion years. And the light that was released in that moment is still traveling. It is still moving. It has been moving for nearly 14 billion years, crossing the expanding universe in every direction. And some of it, the light that was released in our direction, is arriving here, now, at Earth, right now, as we lie here beneath the imaginary stars and breathe slowly in the quiet night. That ancient light surrounds us. It fills all of space. It comes from every direction equally, a soft and ancient glow that is the oldest thing in the observable universe, the first light that ever traveled freely, the memory of the moment the cosmos became transparent. Astronomers have a name for it. They call it the cosmic microwave background. And it is, in a very real and literal sense, a photograph of the universe as it was 380,000 years after everything began. A baby picture of reality itself. We will spend a lot of time with this ancient light in the pages ahead, because it is inside this ancient light, this gentle relic glow of the early universe, that the mystery we have come here to explore is hiding. Something is written in that ancient light, something large and cold and strange, something that should not be there, something that has been quietly astonishing the scientists who have discovered it for many years. But for now, simply stay with the idea. Light remembers. The universe preserves its history in the light it sends outward. And the oldest light in existence, the first light, the light that was born when the universe first became transparent, is still with us, still arriving, still carrying its ancient message. Breathe. Let that settle. There is time. Close your eyes, if they are not already closed, and picture yourself looking outward from the earth. Not from the ground, not from beneath the weight of the atmosphere, but from some imaginary vantage point just above it all, where the air thins and the darkness of space begins, where the boundary between our world and the wider universe feels less like a ceiling and more like an open door. You are looking outward, and as you look, you see the moon, and beyond it the sun, and beyond that the scattered planets, and beyond those the nearest stars, faint and steady in the dark. And beyond the nearest stars, and more beyond those, and the whole vast spiral of the Milky Way spreading around you in every direction. And beyond that, beyond our galaxy are other galaxies, hundreds of billions of them scattered through space in patterns of breathtaking complexity, gathered into clusters and superclusters and vast filaments that stretch for hundreds of millions of light years before dissolving back into the emptiness between structures. And beyond those galaxies, more galaxies still, fainter, older, farther away, their light redder and more stretched because it has been traveling so long and the universe has been expanding all the while, stretching the light as a rubber band stretches when you pull it, making each wave longer, redder, cooler. And at some point, in your imaginary outward gaze, you reach a limit. Not because space ends there, not because there is a wall or a boundary or an edge in any physical sense, but because the light from beyond that point has not had enough time to reach you yet. The universe is a finite age. Light travels at a finite speed, and these two finite things together create a horizon, the edge of what we can see, the boundary of the observable universe. Beyond that horizon, we know nothing. The universe almost certainly continues. There is no reason to think that space simply stops at the point where the light stops arriving. But we cannot see what lies beyond, because no signal, no information, no light of any kind from beyond that horizon has had the billions of years of travel time needed to reach us. We are, in a very real sense, surrounded by an ocean of darkness that is not emptiness but simply unreachable, a darkness not of absence, but of delay. The radius of the observable universe, the distance to that horizon, is approximately 46 billion light-years in every direction. This is larger than you might expect for a universe that is only 13.8 billion years old, and the reason is expansion. The universe has been growing all the time that light has been traveling, so the regions that emitted the oldest light are now much farther away than they were when they emitted it. The light has been chasing an expanding target, and the target has moved. But within that horizon, within our bubble of the observable universe, there is a vast wealth of structure and history to explore. And among all the things that can be observed within that bubble, there is one that stands apart as the most ancient, the most informative, and the most mysterious. It is the light that was released when the universe first became transparent, the light that has been traveling for nearly 14 billion years, the light that fills all of space equally from every direction. The cosmic microwave background. The first light. This ancient glow sits at a very particular distance from us. It sits at what astronomers call the surface of last scattering, the shell around us in every direction that marks the boundary of the opaque early universe. When we look out to the very edge of what we can see, farther than any galaxy, farther than any quasar, we encounter this ancient wall of light, this fossilized glow of the universe's first 380,000 years. And it tells us things about those earliest moments that no other observation possibly could. The surface of last scattering is not a place in any ordinary sense. It is a moment in time, projected onto the sphere of our cosmic horizon. When we look in any direction in the sky and receive this ancient microwave light, we are not looking at a particular location in space. We are looking at a particular moment in time, the moment when the universe cooled enough for atoms to form and light to travel freely. We are seeing the universe at 380,000 years of age, from every direction simultaneously, as though we were standing at the center of an enormous cosmic egg and looking at its inner surface. This is a strange and beautiful thing to hold in your mind. In every direction you look, if your eyes could detect microwaves, you would see the same ancient glow, the same temperature, the same age, the same moment of cosmic childhood looking back at you from every point on the sky. The universe, at its earliest observable stage, appears remarkably the same in every direction, remarkably smooth, remarkably uniform. And this uniformity, this smoothness, is itself one of the great mysteries and triumphs of modern cosmology, because it should not exist. Different parts of the early universe, parts so far apart that light could not have traveled between them in the time available, somehow managed to be at almost exactly the same temperature. How could regions that had never been in contact with each other come to look so similar? How could the universe have coordinated itself so perfectly across distances too large for any signal to cross? The answer to that question led to one of the most important and radical ideas in the history of science, an idea called inflation. We will return to inflation in detail as we go deeper into this story, because it is central to understanding the mystery we are building toward. For now, it is enough to know that inflation is the proposed solution to the mystery of the universe's smoothness, and that the cold anomaly we are eventually going to find in the ancient light is, in a profound and troubling way, a challenge to that solution. But we are not there yet. We are still at the edge of sight, looking outward, understanding the horizon, feeling the shape of the observable universe around us. Take a breath. Let the scale of it settle. You are lying beneath the stars, and the stars you can see are only the nearest lights in a structure that extends 46 billion light years in every direction. And at the very edge of that structure, there is a glow, an ancient, gentle, omnipresent glow, the first light. And in that first light, something is waiting. Something cold and large and strange, and possibly the most important thing human beings have ever discovered. We will find it together. But first, we need to understand what the first light is supposed to look like, so that when we find the thing that is wrong with it, we will understand exactly why it matters so much. Rest now. Let the edge of sight become the edge of sleep. The universe is patient. The ancient light has waited billions of years. It will wait a little longer while you breathe. Before the first light, there was something we struggle even to describe, because the words we have for things depend on the existence of space and time. And what we are trying to describe is the origin of space and time themselves. This is where language begins to strain against the edges of what it was built to contain. But let us try, gently and without hurry, to feel our way toward it. Imagine not the absence of everything, because even absence implies a space in which something is absent, a container waiting to be filled. Imagine instead the complete non-existence of the container itself. No space, no time, no before and no after, no here and no there, nothing from which anything could emerge, and yet something did. This is the deepest mystery that exists, and it is not one that science has yet solved, or perhaps can ever fully solve. The question of why there is something rather than nothing, why the universe exists at all rather than not existing, is a question that sits at the boundary between physics and philosophy, and perhaps beyond both. We do not know the answer. What we know, or at least what the evidence very strongly suggests, is what happened after the something began. Approximately 13.8 billion years ago, in what we call the Big Bang, the universe came into existence. But this name, the Big Bang, is in some ways misleading. It suggests an explosion, something bursting outward from a central point into a surrounding emptiness. But that is not what happened. There was no surrounding emptiness, because there was no surrounding anything. The Big Bang was not an explosion in space. It was an expansion of space. Space itself came into existence and immediately began to grow, carrying with it everything that would eventually become the universe we inhabit. In the first fraction of a second after this beginning, the universe was incomprehensibly hot and incomprehensibly dense. Not hot and dense like the inside of a star, which is itself beyond ordinary experience. Hot and dense in a way that makes the inside of a star seem cool and spacious. The entire observable universe, everything you can see in any direction, everything that exists within the 46 billion light-year bubble around us, was compressed into a region so small that no unit of measurement we use in everyday life is adequate to describe it. And it was expanding. From that first instant, space was growing, and as it grew, it cooled. The energy that had been packed into that impossibly small initial state spread out as the volume of the universe increased. And as it spread out, the universe went through a series of transformations, phase transitions, moments when the state of everything changed in ways that had profound consequences for what the universe would eventually become. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur throughout all of space. Not just in stars, but everywhere in the entire cosmos. Protons and neutrons combined to form the first atomic nuclei, mostly hydrogen and helium, the simple elements that would eventually become the raw material of everything else. This primordial nucleosynthesis, this universe-wide nuclear furnace, lasted only a few minutes before the universe cooled enough for it to stop. What emerged from those few minutes was a universe whose composition, roughly 3/4 hydrogen and 1/4 helium, has shaped everything that followed. But after those first few minutes, the universe remained opaque for a very long time. The nuclei that had formed were still surrounded by free electrons, a plasma of charged particles that scattered light constantly. A photon born anywhere in this early universe could not travel far before being absorbed and re-emitted. The universe was brilliant, flooded with light, but that light was trapped, unable to move more than a tiny distance before being intercepted. For 380,000 years, this continued. The universe expanded, cooled, filled with this trapped light, and waited for the moment when the temperature would drop enough for something new to happen. And then, gradually, the moment came. As the temperature fell below about 3,000 degrees, the electrons in the plasma slowed enough to be captured by the nuclei. Neutral atoms formed. Hydrogen atoms, stable and transparent, replaced the charged plasma. And as the last of the plasma converted to neutral gas, the fog lifted. The universe became transparent. For the first time in its history, light could travel freely. The photons that had been trapped in the plasma were released all at once, streaming outward in every direction into the newly open cosmos. This was the moment we call recombination, and it was the moment when the first light was born. That first light, that release of trapped radiation from the moment of recombination, has been traveling ever since. It has crossed the entire observable universe, expanding and cooling as it goes, its wavelength stretched by the expansion of space from the wavelengths of visible light to the longer, cooler wavelengths of microwaves. What started as a brilliant, hot glow is now a faint, cold bath of microwave radiation, so cool that it registers at just under 3 degrees above absolute zero, the coldest possible temperature. This is the cosmic microwave background, the CMB, the first light that ever traveled freely through the universe, still with us today, surrounding us, filling all of space, arriving from every direction equally. It is the echo of creation, the afterglow of the Big Bang, the oldest thing that can be directly observed. When you hold this in your mind, when you really let it settle, there is something almost unbearably moving about it. The universe's first cry, the first light it ever released freely into itself, is still sounding. It has not stopped. It has not faded into silence. It is quieter now, cooler, stretched thin by billions of years of cosmic expansion, but it is still here, still present, still arriving. And it carries within it, encoded in its temperature and its distribution across the sky, the memory of what the universe was like at the very beginning of its visible history. We are, in a very literal sense, bathed in the memory of creation. Right now, as you lie here breathing, as the night holds you and the imaginary stars glow above, a rain of ancient photons is falling on you from every direction. They pass through you without interaction, the way most things pass through most things in a universe that is overwhelmingly made of empty space. But they are there. The first light is there, always, everywhere, coming from the edge of everything. And in that ancient, everywhere light, something is wrong. Something we will find together in the pages ahead as we learn first to read the light itself, to understand what it should look like, so that the thing that is wrong will show itself to us with all the weight it deserves. For now, breathe. Feel the ancient light around you. Let the warmth of that idea, that creation is still speaking, still sending its first message, that the universe has never stopped saying its first word, settle into your body and quiet your thoughts. The first cry of the universe is still ringing. And somewhere in it, there is a bruise. Every family has photographs, boxes of them, or these days collections of digital files, images that capture moments that would otherwise be lost, moments that show us what things looked like before time changed them. A photograph of a parent as a child, before the gray hair and the lines around the eyes, before all the years of experience settled into their face. A photograph of a city before the buildings that now define its skyline were built. A photograph of a coastline before a storm reshaped it. These images are documents. They are evidence. They show us what was, so that we can understand how we arrived at what is. Science works the same way. When scientists want to understand how something came to be, one of the most powerful things they can do is find an image of that thing early in its history and read that image carefully. And when it comes to the universe itself, the cosmic microwave background is exactly that. It is the earliest image of the universe that physics allows. It is the baby picture of everything. But it is a strange kind of photograph. It does not show us galaxies or stars or any of the structures we associate with the universe as it is today. Those things did not exist yet when this image was made. 380,000 years after the Big Bang, the universe contained no stars, no planets, no galaxies, no structure of the kind we are familiar with. There was only gas, an almost unimaginably vast ocean of hydrogen and helium gas, filling all of space, slowly cooling, still faintly glowing with the warmth of its own early history. What the baby picture of the universe shows us is that gas, its temperature, its distribution across space, where it was slightly warmer and slightly denser, and where it was slightly cooler and slightly less dense. And the word slightly, in this context, deserves emphasis because the differences in temperature across the early universe were extraordinarily small. The average temperature of the cosmic microwave background today is approximately 2.73 degrees above absolute zero. And across the entire sky, across all 400 billion square degrees of the celestial sphere, that temperature is almost perfectly uniform, almost perfectly the same everywhere you look. The variation from the average, the tiny fluctuations above and below that mean temperature, are typically of the order of 100,000th of a degree. 100,000th, not 1 degree, not 1/10 of a degree, 100,000th. To put this in perspective, imagine a room where the temperature everywhere is exactly 20 degrees, and then someone tells you that there are places in the room that are a tiny fraction of a degree warmer or cooler. You would not feel those variations. You could not perceive them. Only an extremely sensitive thermometer could detect them. The cosmic microwave background is like that room. On any ordinary scale, it looks perfectly uniform. It takes the most sensitive instruments ever built to see the tiny wrinkles in that smoothness. And yet those tiny wrinkles are everything. Those barely perceptible variations in temperature across the ancient sky are the seeds of all structure in the universe. The regions that were very slightly denser than average in the early universe had very slightly stronger gravity. Over hundreds of millions of years, that slightly stronger gravity pulled in slightly more gas, which made those regions slightly denser still, which strengthened their gravity further, which pulled in more gas, and so on, in a cascade of gravitational collapse that eventually produced the first stars, the first galaxies, the first clusters and superclusters of galaxies, the entire vast web of cosmic structure that we see today. Everything you have ever known, every mountain and ocean and city and sky, every person you have ever loved, every thought you have ever had, traces its origin back to those tiny, barely perceptible variations in the temperature of the baby universe. The slightly warmer patches became denser. The denser regions became stars. The stars became everything. This is what makes the cosmic microwave background so extraordinary as a document. It is not just a record of what the early universe looked like. It is the blueprint from which all of cosmic history was drawn. Read it correctly, and you can understand not just where we came from, but how and why the universe looks the way it does today, why galaxies are distributed the way they are, why clusters form where they form, why the web of cosmic structure has the particular pattern it has. The CMB is the Rosetta Stone of cosmology. A single image, written in the language of temperature and encoded in the oldest light in existence, that unlocks the entire history of the universe from its earliest moments to the present day. but it is a delicate document. The fluctuations in it are so small, so subtle, that reading them requires instruments of extraordinary sensitivity, instruments that must be shielded from almost every possible source of contamination. Because almost anything, the warmth of the instruments themselves, the emission from the Milky Way, the faint radiation from other galaxies, can swamp the tiny signal we are trying to measure. For most of human history, the cosmic microwave background was not known to exist. It was predicted theoretically in the 1940s, a consequence of the Big Bang model that the universe should have expanded and cooled from a hot, dense state, and should have left behind exactly this kind of relic radiation. But predicting something and measuring it are different things, and for nearly 2 decades after the prediction, no one had the technology to detect this faint ancient glow. Then, in 1964, it was found. Not by scientists specifically looking for it, but by 2 engineers at Bell Telephone Laboratories in New Jersey named Arno Penzias and Robert Wilson, who were trying to use a large horn-shaped antenna to receive signals from a communications satellite. They kept finding a persistent, inexplicable noise in their receiver, a hiss that was the same in every direction they pointed the antenna, that persisted at all times of day and all seasons of the year, that could not be attributed to any known source of interference. They even wondered if pigeons nesting in the antenna were responsible, and they went to some effort to remove both the pigeons and their droppings from the equipment. The hiss remained. It was not the pigeons. It was the universe itself, whispering. It was the first light, the oldest light, the baby picture of everything, arriving at their antenna from every direction equally, a faint and patient signal that had been traveling for nearly 14 billion years and had finally found someone listening. Penzias and Wilson had discovered the cosmic microwave background. They were awarded the Nobel Prize in Physics in 1978 for this discovery, one of the most important in the history of science. And in the decades that followed, the study of this ancient light became one of the central endeavors of modern cosmology. Because the baby picture of everything, once found, demanded to be read. And reading it, it turned out, would reveal not only the history of the universe, but also something deeply, profoundly strange, something that sits in the oldest light like an ancient scar that refuses to fade. We are nearly at the moment of finding it. But first, we need to understand how we built the instruments to read the baby picture properly, how we turned a faint whisper of microwave radiation into a detailed map of the infant universe, how we made the invisible visible and the ancient comprehensible. Breathe slowly. Let the warmth of the idea that the universe kept its baby picture, that it preserved the record of its earliest moments in a light that still surrounds us, settle into you like warmth, like the feeling of being known. The universe made an image of itself at the beginning and never let it go. And in that image, there is something extraordinary waiting, something that will take us to the edge of everything we thought we knew, and perhaps a little way beyond. Rest. The ancient light is everywhere around you. You are already inside the photograph. There is a sound that the universe makes. Not a sound you can hear with your ears, because sound requires air and space has none. But if you could convert the cosmic microwave background into something audible, it would sound something like a very faint, very steady hiss. A soft and ancient noise with no beginning and no end, coming from everywhere at once, filling every corner of existence with the memory of the first moments. This glow, this oldest of all radiations, does not come from any particular place. That is one of the most disorienting things about it for anyone encountering it for the first time. When you look at a star, you can point to it. When you look at a galaxy, you can draw a line from your eye to the place in the sky where it sits. But the cosmic microwave background does not work that way. It comes from everywhere, from every direction simultaneously, from above and below, and to the left and to the right, and from every angle in between. It saturates space the way warmth saturates a room with a fire burning in it, present everywhere, coming from no single point, but filling all available volume with its presence. This is because we are inside it. The cosmic microwave background is not something we observe from outside, the way we observe a distant galaxy. It is something we are surrounded by. We are inside the ancient light. The surface of last scattering, that shell of the early universe from which the first light was emitted, surrounds us in every direction, and its glow reaches us equally from all sides. We float at the center of a sphere of ancient fire, feeling its warmth in frequencies our bodies cannot perceive, but instruments can. And this everywhere quality, this isotropy, this sameness in all directions, is one of the first and most important things that the cosmic microwave background tells us about the universe. The universe, at the time this light was emitted, was extraordinarily uniform. The same temperature, the same density, the same conditions, in every direction as far as the light can tell us. A smoothness that borders on the uncanny, because there is no obvious reason why regions of the universe that were so far apart from one another, regions so distant that light could not have traveled between them in the time available since the Big Bang, should have the same temperature. This puzzle is called the horizon problem, and it is one of the central mysteries that the theory of inflation was invented to solve. But before we get to inflation, before we get to the explanation, let us stay a little longer with the discovery itself, with the remarkable story of how human beings first realized that this ancient light existed and then spent decades building instruments sensitive enough to read it properly. The discovery of the cosmic microwave background by Penzias and Wilson in 1964 was, in one sense, the confirmation of the Big Bang model of cosmology. Before that discovery, there were two competing theories about the origin of the universe. The Big Bang, which said the universe had a beginning, a hot, dense state from which it expanded and cooled, and the steady-state theory, which said the universe had always existed in roughly its current form, with new matter continuously created to fill the space left by expansion. The discovery of the CMB, the relic radiation predicted by the Big Bang model, was a powerful blow to the steady-state theory. Here was the baby picture. Here was the evidence of the beginning. But a confirmation is not the same as a complete understanding. Knowing that the ancient light existed was only the beginning. The next challenge was to read it, to measure it with enough precision to extract the detailed information encoded in its temperature fluctuations, the tiny variations that tell us about the density variations in the early universe, the seeds from which all cosmic structure grew. And this was enormously difficult. The fluctuations are so small, remember, that they are of the order of 100,000th of a degree against a background of nearly 3 degrees. Measuring temperature differences at that level of precision, from the Earth's surface, where the atmosphere itself glows in the microwave frequencies and contaminates the signal, seemed almost impossible. The only way to do it properly was to go to space. To lift an instrument above the atmosphere, above the contaminating glow of the Earth's own warmth, and let it scan the entire sky from orbit, building up a map of the ancient light one careful measurement at a time. This was the mission of the Cosmic Background Explorer, COBE, launched in 1989 by NASA. COBE was not the first instrument to study the CMB, but it was the first with the sensitivity and sky coverage needed to make a genuine map of the temperature fluctuations across the whole sky. And in 1992, the COBE team announced their results, and the announcement caused a sensation in the scientific world and beyond. The satellite had seen the fluctuations. The tiny temperature variations predicted by the Big Bang model, the 100,000th of a degree ripples in the otherwise uniform ancient light, had been detected and mapped. The baby picture had been developed, and it showed, for the first time, the seeds of all cosmic structure, the tiny variations in density that would eventually grow into everything we see in the universe today. The team leader, George Smoot, described the result as like seeing the face of God. It was an extravagant statement, but the feeling behind it was understandable. For the first time in human history, we were looking at a direct image of the universe's earliest moments. The physical record of conditions that existed 380,000 years after the beginning of time. But COBE's resolution was limited. Its map was blurry by the standards that would eventually be achieved. The fluctuations it detected were real and important, but the image it produced was not sharp enough to reveal the fine details that cosmologists needed to test their theories precisely. It was like seeing a photograph that is clearly recognizable, but still slightly out of focus. You can tell what it is. You can read its broad features. But the finer details remain unclear, and it is in the finer details that the most important information often hides. The universe was whispering its oldest secrets, and the instruments needed to hear them clearly were still being built. Stay with this for a moment. There is something beautiful about the image of scientists around the world, through decades of work, building instruments of increasing delicacy and precision, all in pursuit of a clearer picture of the oldest light in existence. A light that has been traveling since before the first star ever burned. A light that carries within it the memory of conditions we can never recreate, never visit, never experience except through the patient decoding of its faint message. The universe kept its baby picture, and we spent decades learning how to see it properly. Breathe. Let the sound of the ancient light, that imaginary, everywhere hiss of creation, settle around you like the quietest possible music. It is playing right now. It has never stopped. A map is a remarkable thing. It takes a space that is too large to hold in the mind all at once, too vast to walk around and look at from every side, and it compresses it into something you can hold in your hands. Something you can trace with your finger, something that lets you see the whole and the parts simultaneously. A map of a city lets you understand how the streets relate to each other, where the center is, how the neighborhoods are arranged, how the rivers or hills or coastlines shape the pattern of everything built around them. A map of a country shows you its borders and its interior, its mountains and its plains, the rivers that define its regions. A map of the infant universe shows you the seeds of everything. When COBE produced the first true map of the cosmic microwave background, it was a map like no other ever made. Not a map of a place, exactly, but a map of a moment. A map of the entire observable universe at the age of 380,000 years, spread across the sky in a projection that tried to flatten the celestial sphere onto a surface we could look at the way we look at a globe of the Earth unfolded into a flat representation. The map showed a sky that was, at first glance, almost perfectly smooth. A warm, nearly uniform glow, reddish in the color scheme scientists chose to represent slightly warmer than average, bluish where it was slightly cooler, and for most of its area, an undifferentiated, peaceful, almost boring uniformity that spoke to the extraordinary sameness of the early universe. But the fluctuations were there. The tiny temperature variations, the seeds of cosmic structure, were visible in the COBE map as a faint mottling of the otherwise smooth background, a barely perceptible texture, like the very slight irregularity of a piece of paper that looks flat until you hold it at an angle to the light. These variations were real. They were not noise. They were the genuine, primordial imprint of the density fluctuations that existed in the universe 380,000 years after the beginning. And they told a story. The story they told was consistent with a universe that had undergone a period of extraordinarily rapid expansion in its very earliest moments. an expansion so fast and so smooth that it had ironed out almost all of the irregularities that might otherwise have existed, leaving behind only the quantum mechanical fluctuations that are the unavoidable consequence of the uncertainty that governs the very small. These quantum fluctuations, tiny random variations at the most fundamental level of physical reality, had been stretched and amplified by the expansion of the universe to become the large-scale structure seeds we see in the CMB map. This story, this explanation of where the fluctuations came from and why they have the particular pattern they have, is the story of inflation. And COBE's map was the first real test of that story, the first observational check against the theoretical predictions. The map matched. The pattern of fluctuations was consistent with what inflation predicted. Cosmology had not only found the baby picture of the universe, it had found evidence that the universe's infancy had included an episode of violent, extraordinary, almost incomprehensible growth. But COBE's resolution was not sharp enough to see the finest details. The map it produced was accurate in its broad features, but blurry at smaller scales, and the smaller scale features were crucially important for the most precise tests of cosmological theory. A sharper map was needed. A map that could resolve the fluctuations down to much smaller angular scales, that could capture the fine structure of the ancient light in all its detail. This was the mission of the Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001. Named for David Wilkinson, one of the pioneers of CMB research, WMAP spent 9 years scanning the sky from a position about 1.5 million kilometers from Earth, far enough from our planet to escape most of the contaminating radiation that would interfere with the delicate measurements. It produced maps of the cosmic microwave background with 30 to 40 times better resolution than COBE, mapped sharp enough to see individual features just half a degree across, roughly the angular size of the full moon in our sky. What WMAP saw, when it looked at the ancient light with this new clarity, was extraordinary. The map that emerged from years of patient data collection was not the blurry, mottled hint of structure that COBE had produced, but a detailed, complex, beautiful image of the infant universe, full of swirls and patches and subtle textures that told a rich and complicated story about what the universe was like and how it had come to be. The WMAP map confirmed the broad features of the COBE result. The universe was indeed remarkably uniform at early times. The fluctuations were indeed of the kind predicted by inflation. The overall pattern was consistent with the standard model of cosmology, the set of equations and parameters that describes the universe we live in. But at higher resolution, new features became visible, features that could be used to measure the properties of the universe with extraordinary precision, to determine the age of the universe, the proportions of ordinary matter and dark energy, the geometry of space itself. WMAP turned the study of the cosmic microwave background from a broad confirmation of the Big Bang model into a precision science. And it set the stage for an even more ambitious effort that would follow a decade later, one that would produce the sharpest map of the ancient light ever made, and that would, in doing so, bring the anomaly we have been building toward into unprecedented focus. But before we get there, let us stay for a moment with the map itself, with the image of the infant universe spread across the sky in its subtle, beautiful, almost but not quite perfect uniformity. Think about what it means to look at something that old. Think about what it means to have an image, a genuine observational record, of conditions that existed 380,000 years after the beginning of everything. Every galaxy you have ever seen in a photograph was not yet born when this image was made. The sun did not exist. The earth did not exist. Life did not exist. Nothing that we would recognize as a star or a planet or any kind of structure had yet formed. There was only the gas, the cooling, gently fluctuating gas, spread across the expanding universe, quietly waiting for the billions of years of gravitational collapse that would eventually produce the world we know. And in the map of that gas, in the pattern of those temperature fluctuations, written in light that is now nearly 14 billion years old, is the information that cosmologists use to test their theories of the universe's birth and early development. The map is a document, a record, a baby picture taken at the moment of the universe's first transparency, preserved in traveling light, and decoded by the patience and ingenuity of human beings who could not let the universe's oldest mystery go unexamined. Something in that is deeply moving. The universe made an image of itself, and we found it, and we learned to read it. Breathe slowly. Let the map of the infant universe settle in your mind like a map of somewhere beloved, like the feeling of knowing a place intimately enough to picture its contours when you are far away. The universe is far away in time, unreachably far, but the map is here. The light is here. The record is here. And on that map, there is a mark, an anomaly, something that should not be there. Something cold and large and strange that has been waiting patiently in the oldest light for billions of years for someone to notice it, to name it, to try to understand it. We are almost there. Imagine that you have been handed a photograph. Not a digital image on a screen, but a physical photograph, the kind that can be held and turned and examined from different angles. The photograph is of a crowd of people, a large gathering in an open space, taken from far enough away that individual faces are not quite distinguishable. You can see that there are many people. You can see the general shape of the crowd, where it is dense and where it thins toward the edges. You can see that the lighting is roughly even, that the people are dressed in similar ways, that the scene is broadly uniform. But there is something in one corner of the photograph that catches your eye. A region that seems somehow different, somehow off, though the resolution is not quite sharp enough to tell you exactly what you are seeing. It might be a shadow. It might be a gap in the crowd. It might be nothing at all, an artifact of the photographic process, a quirk of the light. You stare at it. You turn the photograph. You try to decide if what you are seeing is real or illusory. But the image is not sharp enough to give you a definitive answer. You need a better photograph. This was exactly the situation that cosmologists faced after COBE produced its first map of the cosmic microwave background in the early 1990s. The map was real and important and confirmed the broad predictions of the Big Bang model. But its resolution was limited. The features in the ancient light were visible only as broad, blurry patches, too smeared to reveal the fine details that the most precise tests of cosmological theory required. And in certain regions of that blurry map, there were hints of things that did not quite fit, anomalies that might be real or might be artifacts that could not be confirmed or denied without a sharper image. WMAP was the sharper image. Launched in June of 2001, it spent 9 years at a gravitationally stable point in space called the second Lagrange point, where the gravitational pulls of the Earth and the Sun balance in a way that allows a spacecraft to remain in a fixed position relative to the Earth while orbiting the Sun. From this stable vantage point, far from the contaminating warmth of the Earth, WMAP scanned the entire sky over and over, building up a detailed map of the ancient light one careful measurement at a time. The maps that WMAP produced over its years of operation were released in stages, each one sharper and more detailed than the last as more data accumulated and the analysis techniques improved. The final WMAP data release, the 9-year map, was a document of extraordinary precision, a representation of the temperature fluctuations in the cosmic microwave background at an angular resolution of about 1/4 of a degree, fine enough to see features that had been completely invisible in the COBE map. What those features showed was a universe that was, in its statistical properties, remarkably consistent with the predictions of the inflationary model. The pattern of temperature fluctuations, analyzed in terms of their spatial frequencies, their power on different angular scales, matched the theoretical predictions with a precision that was, in the words of more than one cosmologist, almost embarrassingly good. The universe appeared to have been made according to the simplest possible version of the inflationary recipe. But not quite. Not entirely. Because as WMAP's maps became sharper and sharper, and as the statistical analysis became more and more sophisticated, certain features of the data began to attract attention. Anomalies. Departures from the expected, smooth, random-looking pattern that the simplest inflationary models predicted. Features that were too large, or too aligned, or too extreme to fit comfortably within the standard framework. Some of these anomalies were subtle, requiring careful statistical analysis to establish their reality. Some were more obvious, visible to a careful eye even in the raw maps. And one of them, one that had actually been hinted at in the COBE data, but could not be confirmed with that instrument's lower resolution, stood out from all the others in its size, its significance, and the sheer difficulty of explaining it away. There was a region of the sky, a large region, covering an area of several degrees in the direction of the constellation Eridanus, in the southern part of the sky, where the temperature of the cosmic microwave background was significantly lower than it should be. Not lower by the tiny 1/100th of a degree variations that were the normal fluctuations of the CMB. Lower by a significantly larger amount. Lower in a way that was statistically anomalous, that could not easily be attributed to the random fluctuations expected from the standard model. It was cold. Conspicuously, inexplicably, stubbornly cold. And it was large. Not a point, not a small patch, but a region spanning several degrees of sky, covering an area about 5 times the size of the full moon as seen from Earth. Which, given that this ancient light comes from a distance of approximately 46 billion light-years, means that the physical size of the cold region in the early universe was genuinely enormous. Hundreds of millions of light-years across. Perhaps larger. Scientists noticed it. They noted it in their papers. They flagged it as an anomaly, something that deserved further investigation. But WMAP's resolution, while dramatically better than COBE's, was still not the sharpest possible. The anomaly was real, but its precise extent and depth could not be determined with confidence. What was needed was, again, a sharper image, a more precise instrument, a more careful measurement. The best photograph of the ancient light had not yet been taken. It was being planned. It was being built. It was going to be launched into space and pointed at the sky and asked to see the oldest light with the clearest possible eyes. And when it was, the cold region would come into focus with a clarity that left no room for doubt. The anomaly was real. The ancient scar was there. And it was stranger than anyone had quite expected. Breathe. Feel the sharpening, the slow clarification, the patient process of building better and better instruments to see more and more clearly what has always been there, written in the oldest light, waiting. There is something deeply human about that process. The refusal to accept a blurry image when a sharper one might be possible. The drive to see more clearly, even when what you might see clearly could be unsettling. The picture is getting sharper. The cold region is coming into focus. In the history of science, there are instruments that define an era, not because they are the first to detect something, but because they detect it with such precision, with such unambiguous clarity, that what was previously a hint or a suggestion or a possibility becomes a fact. A measurement that cannot be argued away. A result that sits in the literature with the quiet authority of something that has been tested from every angle and has refused, each time, to disappear. The Planck satellite was such an instrument for the cosmic microwave background. Launched in 2009 by the European Space Agency, named for the physicist Max Planck, whose work on radiation was foundational to quantum mechanics, the Planck satellite spent more than 4 years at the second Lagrange point, scanning the entire sky with detectors of extraordinary sensitivity. The goal was to produce the definitive map of the cosmic microwave background, the sharpest, most detailed, most precisely calibrated image of the ancient light that current technology could achieve. The Planck satellite had several advantages over its predecessors. It operated at lower temperatures, which reduced the thermal noise in its detectors. It had more detector channels, sensitive to more frequencies of microwave radiation, which allowed better separation of the genuine CMB signal from the foreground contamination produced by the Milky Way and other nearby sources. It had better angular resolution, capable of distinguishing features as small as about 5 arc minutes, roughly 1/10 of a degree, far sharper than anything previously achieved. The first full sky map from Planck was released in 2013, and it was, by any measure, a masterpiece of scientific instrumentation and analysis. A map of the entire sky at a resolution and precision that made the WMAP maps look, by comparison, like the COBE maps had looked against WMAP. Each step upward in resolution revealing new detail, new texture, new information in the ancient light. Each new map a sharper baby picture, a clearer photograph of conditions that existed 380,000 years after everything began. The Planck map confirmed, with even greater precision than before, the overall picture that COBE and WMAP had established. The universe was indeed nearly uniform at early times. The fluctuations were indeed consistent with inflation. The parameters of the standard cosmological model, the proportions of ordinary matter and dark energy, the age and geometry of the universe, were all measured with unprecedented accuracy. Cosmology had arrived at what some called the era of precision cosmology, the era when the broad features of the universe's history were known well enough that the interesting questions were about details rather than fundamentals. And yet the Planck map, for all its precision and beauty, confirmed the existence of the anomaly. The cold region, the strange, large, inexplicably cold patch in the southern sky, in the direction of Eridanus, the patch that had been hinted at by COBE and seen by WMAP, was there in the Planck map with a clarity that left no room for ambiguity. Not a blur, not a broad smear of statistical uncertainty, but a distinct and well-defined region, its boundaries sharper than any previous instrument had been able to resolve, its temperature deficit precisely measured for the first time with enough precision to begin putting real constraints on what could and could not explain it. The Planck team were careful in how they described it. Scientists are by nature and training cautious about anomalies. The history of science contains many apparent anomalies that turned out, upon further investigation, to be artifacts of measurement error or analysis mistakes, or simple statistical flukes that happen to occur in any finite dataset, even when the underlying process is perfectly random. An anomaly that disappears when you look more carefully is not an anomaly at all. It is a ghost, and scientists learn to be wary of ghosts. But this anomaly did not disappear when they looked more carefully. It sharpened. The Planck map did not make the cold region smaller or less significant. If anything, it made it more defined, more precisely located, more clearly real. The Planck team noted it in their papers with the careful language of scientists who know that they are looking at something that does not fit the standard model, but who are unwilling to make extraordinary claims without extraordinary evidence. They called it a significant deviation from the predictions of the standard inflationary model. They called it one of the anomalies that posed the most interesting challenges to cosmology. They noted that it had been seen by multiple instruments with different systematic errors, which made it very unlikely to be an instrumental artifact. They noted that it was statistically significant at a level that, in any other field of science, would be considered compelling evidence for a real effect. What they did not do, at least not in those careful official papers, was speculate freely about what it might mean. That speculation was happening, of course, in offices and at conferences and over coffee between scientists who spend their working lives thinking about these questions and who could not resist wondering, even if they could not yet prove, whether the cold region in the ancient light might be telling them something extraordinary about the nature of reality itself. Because the cold region was not just cold. It was cold in a way that was difficult to explain within the standard framework. It was cold in a region that was large enough and cold enough that the most straightforward explanations, the explanations that did not require any radical rethinking of the cosmos, struggled to account for it fully. It was cold in a way that left a door open, just barely, just a crack, for an explanation that was not straightforward at all. But that was, if true, the most remarkable thing that physics had ever discovered. The Planck satellite had done its job. It had taken the sharpest baby picture of the universe ever made. It had confirmed the standard model with extraordinary precision, and it had confirmed, equally precisely, the existence of the ancient scar, the impossible chill, the mark in the oldest light that should not be there. The map was beautiful, and on the map, visible now with a clarity that made evasion impossible, there was a wound. Breathe. Let the sharpening picture settle in your mind. The instruments have done their work. The baby picture is as clear as it has ever been. And the mark is there, cold and large and real. It is time to look at it directly. There is a place in the sky, not a visible place, not somewhere you can find with the naked eye or even with an ordinary telescope, but a place that instruments sensitive to microwave radiation can locate precisely, in the southern celestial hemisphere, in the direction of the constellation Eridanus, the river, which winds its way across the southern sky in a long, irregular chain of faint stars that ancient astronomers imagined as a great celestial waterway. In that direction, in the ancient light of the cosmic microwave background, there is a region that is cold. Colder than it should be. Colder than the standard models of cosmology predict it ought to be. Colder than the random fluctuations of the infant universe, fluctuations which are themselves extraordinarily small, would ordinarily produce. It is cold in a way that is statistically anomalous, that sits at the far tail of the distribution of expected temperatures, that draws the eye even in the raw maps of the ancient light as a region that simply does not fit with everything around it. This is the cold spot, and it has been quietly unsettling cosmologists since it was first identified in the WMAP data in 2004, when a team of researchers led by Kate Land and João Maguejo, examining the distribution of temperature fluctuations across the CMB sky, noted a region in the southern hemisphere of the sky that was anomalously cold and anomalously large. Let us try to understand what we mean when we say cold in this context. Because the absolute temperature differences involved are tiny. The cosmic microwave background has an average temperature of 2.73 degrees above absolute zero. The cold spot is colder than that average, but not by 1 degree, not by 1/10 of a degree, not even by 100th. The temperature deficit of the cold spot is roughly 70 microkelvin, 70 millionths of a degree, below the average temperature of the CMB. This sounds impossibly small, And in everyday terms, it is. No thermometer you have ever held in your hand could detect a temperature difference of 70 millionths of a degree. But in the context of the CMB, where the typical temperature fluctuations are themselves only of the order of 100 microkelvin, a deficit of 70 microkelvin is significant. It is a large fraction of the typical variation. It places the cold spot far out in the tail of the statistical distribution of expected temperature values. Think of it this way. If you were to sample the temperature at millions of random points across the CMB sky, and you plotted the distribution of temperatures you measured, you would get something that looked like a bell curve. Most points would be very close to the average. A few would be somewhat warmer. A few would be somewhat cooler. And at the very extremes of the distribution, you would expect to find a handful of genuinely anomalous values, points where the temperature is significantly different from the mean. The cold spot sits at the cold end of that distribution, not just in the tail, in the far tail, in the part of the distribution where, if the standard model of inflation is correct, you would not expect to find anything of its size. Because it is not just cold, it is also large, and it is the combination of being cold and large simultaneously that makes it so difficult to explain. The cold spot covers an area of the sky roughly 5 degrees across, which sounds modest until you translate it into physical size. Given that the CMB sits at the surface of last scattering, approximately 46 billion light-years away, a region 5 degrees across on that surface corresponds to a physical size of several hundred million light-years. Several hundred million light-years of space that was anomalously cold in the early universe, a region of the infant cosmos that was not just slightly different from its surroundings, but significantly, measurably, stubbornly different. This is the ancient scar. This is the impossible chill. A wound in the first light, an irregularity in the baby picture of the universe that has refused every attempt to explain it away and has sat quietly in the data from WMAP and Planck, growing sharper with each new instrument, waiting for someone to understand it. The discovery of the cold spot prompted an immediate effort to explain it within the framework of the standard model. Scientists are, as we noted earlier, appropriately skeptical of anomalies. The history of cosmology contains examples of apparent anomalies that turned out to be foreground contamination, regions of the sky where emission from the Milky Way or from distant radio galaxies had leaked into the CMB maps and created fake cold or hot spots. Could the cold spot be foreground contamination? This was the first hypothesis to be tested, and the answer, after careful analysis, was essentially no. The cold spot sits in a region of the sky far from the main emission from the Milky Way. It has been seen at multiple frequencies of microwave radiation, and its properties do not change in the way that foreground contamination would. It is genuinely in the CMB itself, not a ghost imprinted by something in our own galaxy. Could it be a statistical fluke? The CMB fluctuations are random in the sense that quantum mechanics is random, and in any randomly fluctuating field, very large, very cold regions can occur by chance. Just as you can flip a coin 20 times and get 15 heads in a row without needing any special explanation. Could the cold spot simply be one of those extremely unlikely but not impossible statistical accidents? The probability calculations are uncomfortable. Depending on how you define the cold spot and how you perform the statistical test, estimates of the probability of finding a feature this cold and this large by chance in the standard inflationary model range from about 1 in 200 to about 1 in 1,000. A 1 in 200 chance is not zero. If you ran the universe 200 times, starting from similar initial conditions, one of those runs might produce a cold spot this extreme just by chance. But we only have one universe. And in that one universe, the cold spot is there, sitting in the oldest light, cold and large and real, with a probability of between 0.5 and 1% of being just a fluke. Those are not compelling odds. In medicine, a treatment that worked 99% of the time would be considered extremely effective. A finding that had only a 1% probability of being a fluke would be considered statistically significant by almost any standard. Something is there. Something real. Something in the fabric of the early universe that made one large region colder than everything around it. Something that the standard model of cosmology, the beautiful, precise, extraordinarily successful standard model that has been confirmed by decades of observation, does not easily accommodate. The ancient scar is real. The impossible chill is there, in the oldest light, waiting to be understood. And the explanations that have been offered for it, the explanations that do not require any radical rethinking of the universe, have so far fallen short. What remains, after the ordinary explanations have been tested and found inadequate, is something extraordinary. Something that, if true, would transform our understanding of what the universe is, what it is part of, and what it means to exist within it. But we are not there yet. First, we must understand why the cold spot is so difficult to explain. We must understand what the standard theory predicts and why the cold spot defies those predictions. We must feel the full weight of the impossibility before we are ready to consider the explanation that would resolve it. Brief. The cold spot is there. It has always been there. In the ancient light, in the baby picture, in the map of the infant universe, there is a mark, cold and vast and patient. Rest now. The universe is patient. The cold region has waited billions of years. It will wait a little longer while you sleep. There is a particular quality to something that refuses to go away. A quality that is different from something that simply persists, different from something that is merely difficult to remove. When something refuses to go away despite every reasonable effort to explain it, despite every tool brought to bear against it, despite every careful attempt to demonstrate that it is not really there or that it is not really significant, that quality becomes something else entirely. It becomes insistence, the insistence of a fact that has decided it will be known. The cold spot has that quality. From the moment it was first identified in the WMAP data, the scientific community did what the scientific community always does with an anomaly. It tried to make it disappear, not out of any desire to suppress an inconvenient finding, but out of the appropriate and necessary skepticism that is the foundation of good science. If you find something strange, the first question is always whether it is really strange or whether it only appears strange because of some error in your measurement, some artifact of your analysis, some subtle mistake in your methodology that, once corrected, will make the apparent anomaly vanish and leave behind only the ordinary, comfortable, well-understood physics you expected. The first line of attack was the question of foreground contamination. The cosmic microwave background is not the only thing emitting microwave radiation in the universe. The Milky Way itself emits microwaves, produced by electrons spiraling around magnetic field lines in the interstellar gas, by warm dust in star-forming regions, by the thermal emission of diffuse ionized gas spread through the galaxy. All of this galactic emission has to be carefully removed from the CMB maps before the primordial temperature fluctuations can be studied. And removing it is not trivial. It requires detailed models of the galactic emission built from observations at multiple frequencies where the galactic signal dominates over the CMB, and it involves subtractions that can introduce errors if the models are imperfect. Could the cold spot be a residual of imperfect galactic foreground removal? Could there be a region of the sky in the direction of Eridanus where the foreground subtraction had overcorrected, leaving behind an artificial cold patch that was not actually present in the primordial CMB at all? This was tested carefully and repeatedly. Scientists used different methods of foreground removal, different models of the galactic emission, different frequency combinations to separate the CMB from the contaminating sources. They looked at the cold spot at multiple frequencies, comparing how its properties changed with frequency, because a genuine CMB feature should look the same at all frequencies while a foreground artifact would change. The cold spot looked the same at all frequencies. It did not change in the way that foreground contamination would. The tests pointed firmly toward the conclusion that the cold spot was real, a genuine feature of the primordial CMB and not an artifact of the foreground removal process. The second line of attack was the question of instrumental artifacts. Any real instrument has imperfections. Detectors have non-uniform sensitivity. Pointing errors can smear features across the sky. Electronic noise can create spurious signals that, if systematic rather than random, could appear as coherent structures in the final map. Could the cold spot be an instrumental artifact, a ghost created by some imperfection in the WMAP or Planck satellites rather than a real feature of the ancient light? This too was tested carefully. The two satellites have completely different designs, different detectors, different scanning strategies, different systematic errors. If the cold spot were an artifact of one instrument, it should not appear in the data of the other. But it appears in both. It appears in the WMAP data, collected over 9 years with one set of detectors and one scanning strategy. It appears in the Planck data, collected over 4 years with a completely different set of detectors and a completely different scanning strategy. The two independent instruments, designed and built by different teams on different continents with different technical approaches, both see the same cold region in the same place in the sky. The probability of an instrumental artifact producing the same spurious feature in two completely independent instruments is essentially zero. The cold spot is not a ghost of the instruments. It is a feature of the sky itself. The third line of attack was the statistical argument. Perhaps the cold spot is simply a fluctuation, an extreme but not impossible random event in the primordial temperature field. We noted earlier that the probability of finding a feature this cold and this large by chance in a standard inflationary universe is somewhere between 1 in 200 and 1 in 1,000, depending on how the statistical test is performed. These are small probabilities, but they are not zero. Scientists argued about the statistics for years. The difficulty is that there is a subtle trap in this kind of analysis called the look elsewhere effect. If you look at a map with millions of pixels and search for anomalous regions, you will inevitably find some, simply because a distribution with many samples will always produce some extreme values. The question is not whether you found an anomalous region. It is whether the anomalous region you found is more extreme than you would expect given that you were searching a large map for the most extreme feature it contained. Accounting for this look elsewhere effect reduces the statistical significance of the cold spot somewhat. But even after this correction, the cold spot remains anomalous at a level that is difficult to dismiss. Multiple groups, using different statistical methods, different ways of defining the cold spot, different approaches to the look elsewhere correction, have reached broadly similar conclusions. The cold spot is a real feature of the CMB. It is more extreme than the standard inflationary model predicts, and its probability of being a random fluctuation, while not vanishingly small, is small enough that it deserves a physical explanation. And here is where the ancient scar earns its name. Because despite years of careful investigation, despite every attempt to explain it away as an artifact or a fluke, the cold spot remains. It has not faded. It has not been explained by better foreground removal or improved understanding of instrumental systematics. Each sharper instrument has only confirmed its existence with greater precision. Each more sophisticated statistical analysis has only reaffirmed its anomalous character. It is a wound in the oldest light that has refused, for decades, to heal. An irregularity in the baby picture that has resisted every interpretation that does not require something genuinely unusual to have occurred in the early universe. The ancient scar is there. It is real. It is not a mistake. It is not a fluke, or at least not probably a fluke. It is something that happened, something that left a mark in the infant cosmos, something that the universe has been carrying in its oldest light for nearly 14 billion years. What happened? That is the question that sits at the heart of this entire journey. And to answer it properly, or at least to understand the answers that have been proposed, we need to understand what the standard model of cosmology predicts, what inflation says the early universe should have looked like, and why the cold spot seems to defy those predictions. We need to understand the impossible chill. Breathe. The scar is there. It has always been there. And the universe, patient beyond any measure of human patience, is waiting for us to understand what made it. Rest. The ancient light is everywhere around you, carrying its oldest mark. And we are listening. To understand why the cold spot is impossible or nearly impossible, within the framework of standard cosmology, we need to spend some time with the theory that was designed to explain why the universe is so smooth in the first place. We need to understand inflation, not in the technical mathematical language of the original papers, but in the way it feels, the way it changes your sense of what the early universe was like, the way it transforms the deepest mystery of cosmological smoothness into something that seems, if not entirely natural, at least explicable. Begin with the horizon problem that we mentioned earlier. The cosmic microwave background is almost perfectly uniform. Regions of the early universe that were so far apart from each other that light could never have traveled between them in the time since the Big Bang. Regions that were in no causal contact whatsoever, nevertheless had essentially the same temperature. How? How could places that had never communicated with each other arrive at the same state? In ordinary physics, this kind of coordination requires contact. Temperature equalizes between two regions when heat can flow between them. The temperature of a room equalizes over time because air can carry heat from the warm parts to the cool parts. But if two regions are completely isolated from each other, if no signal of any kind can pass between them, their temperatures have no reason to be equal unless they started out equal. And the problem is that the regions we are talking about in the early universe did not have time to start out equal through any ordinary process. The universe was so young, and the regions were so far apart, that there was simply not enough time, even at the speed of light, for any causal process to have established the uniformity we observe. The smoothness of the CMB seems to require that the universe was born smooth, that it somehow started with the same temperature everywhere, without any physical process to enforce that equality. This is the horizon problem, and it was one of the central motivations for the theory of inflation proposed independently by several physicists in the late 1970s and early 1980s, most notably Alan Guth in 1980. Inflation proposes that in the very first fraction of a second after the Big Bang, before the era we have been describing, the universe underwent a period of extraordinarily rapid expansion. Not the gradual, steady expansion that has continued ever since, but a violent, exponential growth in which the size of the universe doubled and doubled again and doubled again, over and over, an enormous number of times in an extraordinarily short period. In the most commonly discussed versions of inflation, the universe expanded by a factor of at least 10 to the power of 26, that is a 1 followed by 26 zeros, in a time of roughly 10 to the minus 32 seconds. This is expansion so fast that it is almost impossible to imagine. In that tiny fraction of a second, a region of space so small that it would be invisible under any microscope expanded to a size larger than the observable universe today. A single, smooth, causally connected patch of space, small enough that all its parts had been in contact with each other and had reached the same temperature, was inflated to a size that dwarfed everything we can observe. And this, the inflation model says, is why the CMB is so smooth. Not because different parts of the early universe somehow coordinated their temperatures across impossible distances, but because all the parts of the universe we can observe were once contained within a single, tiny, causally connected region that had equilibrated to a uniform temperature. Inflation then stretched that small, smooth patch to a size much larger than the observable universe, ensuring that everything we can see descended from a region that was essentially uniform. But inflation does more than just solve the horizon problem. It also makes predictions about the pattern of fluctuations in the CMB, because quantum mechanics tells us that no region of space can be perfectly uniform. At the smallest scales, there are always quantum fluctuations, tiny random variations in the energy density of any field. And inflation takes these tiny quantum fluctuations and stretches them, amplifying them from the microscopic scale where quantum mechanics operates to the macroscopic scale of the universe itself. The fluctuations we see in the CMB, the seeds of all cosmic structure, are, according to inflation, the stretched and amplified remnants of quantum mechanical uncertainty. The random, fundamental uncertainty of the quantum world, stretched by the violent expansion of the universe to become the large-scale structure of galaxies and clusters and superclusters. This is a beautiful idea, and the pattern of fluctuations that inflation predicts is very specific. It predicts that the fluctuations should be nearly scale invariant, meaning that they should have roughly the same amplitude on all spatial scales. It predicts that they should be Gaussian, meaning that their statistical distribution should follow the bell curve of random processes. And it predicts that there should be no preferred direction in the fluctuations, that the universe should look the same in all directions on large scales. These predictions have been tested by Cope, by WMAP, by Planck. And the verdict, on the whole, is remarkably good. The fluctuations are nearly scale invariant. They are approximately Gaussian. The universe does look broadly the same in all directions on large scales. The predictions of inflation are confirmed over and over with increasing precision. And then there is the cold spot. The cold spot is, in the language of statistics, an extreme value. It is the coldest large region in the CMB sky. And inflation says that the fluctuations in the CMB should be Gaussian and random, which means that extreme values should be rare but possible. The question is whether the cold spot is too extreme, too large, too cold, to be consistent with the random Gaussian fluctuations that inflation predicts. The answer, as we noted in the previous part, is that it probably is too extreme. Not certainly, not impossibly so, but probably. The cold spot sits in the tail of the distribution at a level that is uncomfortable for the simplest versions of the inflationary model. And what makes it particularly difficult to explain is the combination of its size and its depth. It is not just a large cold region. It is a large cold region that is also significantly colder than random fluctuations of that size would typically be. Imagine tossing a coin thousands of times and recording the results. Occasionally, by chance, you will get a run of heads that is unusually long. But the longer the run, the less probable it becomes. A run of 10 heads in a row is unlikely. A run of 20 is very unlikely. A run of 50 is vanishingly unlikely. The cold spot is like a run of 50 heads. Not impossible, but unlikely enough that it makes you wonder if the coin is fair. The impossible chill is not just cold. It is cold in a way that tests the limits of what the standard model of cosmology can comfortably accommodate. It is cold in a way that says, quietly but insistently, that something might have happened here. Something beyond the ordinary random fluctuations of inflation. Something that left a mark deeper and larger than the standard physics should have been able to produce. What could that something be? There are two main hypotheses. One is a physical structure in the nearby universe, a vast empty region of space, a supervoid, that could have imprinted an extra coldness on the CMB photons passing through it. The other is something far more radical, something that takes us to the edge of the entire framework of modern physics, and perhaps a little way beyond it. We will explore both. First, the supervoid, because before we can appreciate the truly extraordinary explanation, we need to understand why the ordinary one is not enough. The impossible chill is there, cold and large and patient, waiting for its explanation. Breathe. Feel the weight of the anomaly, the gentle, insistent pressure of something real that does not fit the map. There is something clarifying about that pressure. It means the universe still has secrets. It means the story is not over. Rest in that. Space is mostly empty. This is something we know in an abstract way, something we have been told, but the full reality of it is difficult to truly feel. The universe, for all its billions of galaxies and trillions of stars, is overwhelmingly made of nothing. A vacuum, of space that contains no stars, no gas dense enough to see, no planets, no dust, nothing but the faintest wisps of intergalactic medium and the invisible scaffolding of dark matter. Between the stars within a galaxy, the average distance is several light years, and a light year is about 10 trillion kilometers. Between galaxies within a cluster, the distances are millions of light years. And between the clusters and superclusters of galaxies, in the great cosmic voids that make up most of the volume of the universe, the distances between any significant concentration of matter are hundreds of millions of light years. The universe is not a crowded place. It is a vast, mostly empty ocean in which islands of matter, the galaxies and clusters, are separated by stretches of near nothingness that dwarf even the islands themselves. These great empty regions have a name. They are called voids, and they are not merely absences. They are structures in their own right, defined regions of space where the density of matter is significantly below the cosmic average, where galaxies are rare and the intergalactic gas is thin, where the gravitational landscape is dominated not by the pull of nearby matter, but by the outward flow of the cosmic expansion itself. Voids come in many sizes. Small voids of a few tens of millions of light years are relatively common. Larger voids of 100 million light years or more are less common. And supervoids, the largest of the empty regions, can stretch for hundreds of millions of light years, making them among the largest coherent structures in the observable universe. The existence of supervoids is well established. They have been mapped in the distribution of galaxies across the sky. Where a void exists, the density of galaxies drops noticeably, sometimes dramatically, compared to the surrounding regions. The galaxies are still there, on the boundaries and in the walls and filaments that surround the void, but within the void itself, the space between galaxies is much larger than average. Now here is the connection to the cold spot. When CMB photons travel through space on their way from the surface of last scattering to our detectors, they do not travel through a perfectly uniform medium. They travel through the real, lumpy, structured universe, with its clusters and filaments and voids. And as they travel through these structures, their energy is affected by the gravitational landscape they pass through. This effect is called the integrated Sachs-Wolf effect, after the two physicists who first described it in 1967. It works like this. When a photon enters a region of higher than average density, a cluster or a filament, it descends into a gravitational potential well. As it descends, it gains energy and becomes slightly hotter. When it climbs back out of the well on the other side, it loses the energy it gained and returns to its original temperature. In a universe that is expanding but not accelerating, these two effects cancel out perfectly. The photon neither gains nor loses energy overall from passing through a density enhancement. But in our universe, the expansion is accelerating. Dark energy is causing the universe to expand faster and faster over time, and this acceleration changes the calculation. Because the universe expands while the photon is inside the potential well, the well itself becomes shallower during the photon's passage. When the photon climbs back out, it does not have to climb quite as high as when it went in, because the expansion has stretched the well while the photon was inside. The photon gains slightly more energy going in than it loses going out. The photon is heated by passing through a large mass concentration. For voids, the effect is reversed. A photon entering a void is traveling through a region of lower than average density, a gravitational potential hill rather than a well. As it climbs the hill, it loses energy. As it comes down the other side, it regains energy. But again, because the expansion is accelerating and the void grows while the photon traverses it, the photon does not fully recover the energy it lost. The void has grown during the passage, and the photon exits slightly cooler than it entered. A supervoid therefore imprints a cold spot on the CMB, making photons that pass through it appear slightly cooler than photons that did not. This is the void hypothesis for the cold spot. If there is a very large, very deep supervoid in the direction of Eridanus, directly between us and the cold spot in the CMB, then photons from the cold spot region would have had to pass through that void on their way to us. They would have been cooled by the integrated Sachs-Wolf effect, and the cooling would appear in the CMB map as exactly the kind of cold region that we observe as the cold spot. It is a physically reasonable hypothesis. The mechanism is well understood. The integrated Sachs-Wolf effect is a real phenomenon that has been detected in other contexts, in statistical correlations between the CMB and the distribution of large-scale structure. And if there were a supervoid of the right size and depth in the right direction, it would provide a natural, within standard physics explanation for the cold spot that would not require any exotic new ideas. So scientists went looking for the void. They searched the catalogs of galaxies and quasars in the direction of Eridanus, looking for the galaxy deficit that would signal a large empty region in the foreground of the cold spot. And they found something. In 2007, a team led by Lawrence Rudnick used a catalog of radio galaxies to identify a region in the direction of the cold spot where the density of galaxies was noticeably below average. This appeared to be the supervoid that the hypothesis predicted. The announcement attracted considerable attention, with some headlines suggesting that the mystery of the cold spot had been solved. But subsequent investigations complicated the picture considerably. Further surveys of the galaxy distribution in the direction of Eridanus confirmed that there was indeed a region of below-average galaxy density, but the precise extent, depth, and distance of the void became matters of ongoing debate. Different surveys using different tracers of the large-scale structure gave somewhat different answers, and the size and depth of the void that emerged from the data, while real, was not obviously large enough and deep enough to explain the full temperature deficit of the cold spot through the integrated Sachs-Wolf effect alone. The void hypothesis was promising, but the numbers were not quite working out. And this is where the story becomes genuinely interesting. Because the supervoid that observations suggested was present in the direction of Eridanus was a real structure, a genuine empty region of space. but it was a supervoid that fell short. A supervoid that could explain some of the cold, but not all of it. A supervoid that narrowed the gap between observation and prediction, but did not close it. Something was still missing. The void was there, but it was not enough. Think about what that means. There is an anomalously cold region in the oldest light in the universe. There is an anomalously empty region of space between us and that cold region. The empty region cools photons passing through it by a known physical mechanism. But the empty region is not empty enough, not large enough, not deep enough to produce all of the coldness we observe. There is a residual, a chill that persists after the void has been accounted for. An impossible chill. Breathe. The void is there. It is real. It is part of the story. But it is not the whole story. Something more is needed. Something that will take us beyond the edges of the ordinary and into territory that is genuinely, extraordinarily strange. Rest in the incompleteness. The best questions are never fully answered with the first answer. Science is patient in a way that can be hard to appreciate from the outside. It does not rush to conclusions. It does not abandon a hypothesis because the first results are ambiguous, or cling to a hypothesis because the first results are encouraging. It keeps looking, keeps measuring, keeps improving its instruments and its methods and its data, accumulating evidence until the picture becomes clear enough to support a judgment. And the judgment that has accumulated about the supervoid hypothesis for the cold spot is a nuanced one. It is not a clean verdict of proven or disproven. It is something more like a partial credit. The void is real. The mechanism is real. But the numbers do not fully add up. Let us try to understand the shortfall with some concrete numbers. The temperature deficit of the cold spot is approximately 70 to 80 microkelvin below the CMB average. This is the depth of the cold region that needs to be explained. The integrated Sachs-Wolf effect produced by a supervoid depends on the depth of the void, meaning how much emptier it is compared to the cosmic average, and its size, measured in terms of how much space the photons had to traverse while inside it. The supervoid in the direction of Eridanus, the one that has been identified in galaxy surveys, appears to be a real structure. It is genuinely empty, containing significantly fewer galaxies than the cosmic average. It is genuinely large, extending over several 100 million light-years. When astronomers calculate the integrated Sachs-Wolf cooling that this observed void would produce, they get a temperature deficit. But the deficit they calculate is significantly smaller than the observed cold spot. Different groups doing this calculation have gotten somewhat different numbers, reflecting genuine uncertainties in the properties of the void. But the broad conclusion has been consistent across multiple analyses. The supervoid can explain roughly 20 to 40% of the cold spot's temperature deficit, perhaps up to 50% in the most optimistic assessments, but not the full depth of the cold region we observe. There is a gap, a residual coldness that the void cannot explain. A portion of the cold spot's impossibly low temperature that remains after the integrated Sachs-Wolf effect has done all the cooling it can. One possibility is that our measurements of the supervoid are imperfect. Galaxy surveys have limitations. They can only probe the distribution of galaxies that are bright enough to be detected, which may not perfectly trace the underlying distribution of all matter, including dark matter. If the actual void is larger or deeper than our galaxy surveys suggest, if the real distribution of matter in that region of space differs from what we have been able to measure, then the integrated Sachs-Wolf cooling might be larger than our current calculations indicate. In 2015, a team led by Istvan Saputty used data from a new galaxy catalog to argue that the supervoid in the direction of the cold spot was larger and deeper than previous surveys had suggested. They claimed that the revised supervoid was large enough to explain the cold spot entirely through the integrated Sachs-Wolf effect, without needing any additional physics. This claim attracted significant attention and was widely reported as a potential resolution of the cold spot mystery. But the story did not end there. Subsequent analyses found that even the revised supervoid was not quite large enough or deep enough to fully explain the cold spot, at least not without requiring the void to be an extreme structure that was itself statistically improbable. If the supervoid explanation requires a supervoid that is itself anomalously large and deep, you have not really solved the problem. You have only moved it. You have replaced one improbable feature of the CMB with another improbable feature of the large-scale structure. The anomaly has changed its address, but it has not gone away. And there is another problem with the supervoid hypothesis that goes beyond the numbers. The integrated Sachs-Wolf effect not only cools photons passing through a void, it also changes their pattern in a particular way. The cooling profile, the way the temperature deficit varies across the angular extent of the cold region, should have a specific shape when produced by the integrated Sachs-Wolf effect. The shape predicted by a supervoid is a broad, relatively smooth cold region that fades gradually toward its edges. But the cold spot's observed profile does not perfectly match this prediction. The cold spot has been described as having a complex, nested structure, a very cold central region surrounded by a ring of slightly warmer temperatures, surrounded in turn by a broader region of slightly below average temperature. This concentric ring structure is not what you would expect from the integrated Sachs-Wolf effect of a single supervoid. It is, however, remarkably consistent with the profile that a very different mechanism would produce. A mechanism that we will discuss in the parts that follow. But first, stay with the shortfall. Stay with the feeling of a hypothesis that gets you most of the way there, but not quite all the way, that explains much, but not everything, that closes the gap, but not entirely. This feeling, the feeling of a partial explanation, is one of the most important in science. It tells you that you are on the right track. There is something real here, something the void is genuinely contributing to. But it also tells you that the real answer is larger than the explanation you have found so far, that there is still something to understand. The supervoid is part of the story of the cold spot. The integrated Sachs-Wolf effect is part of the story. But there is more. And the more is what makes this one of the most extraordinary open questions in all of modern physics. Brief. The gap is there. The residual chill is there. And on the other side of that gap, waiting to be considered with its full weight of implication and wonder, is an idea so large that it changes not just our understanding of the cold spot, but our understanding of everything. The void falls short. Something else made the mark. Rest. The impossible chill is still there, still waiting. The universe is not done speaking. There is a question that sits beneath all of cosmology, beneath all of physics, beneath even the question of where the universe came from. It is a question so fundamental that simply stating it clearly takes a moment of quiet and care. The question is this: is our universe the only one? For most of human history, this question did not even make sense. The universe was, by definition, everything that existed. The cosmos was the totality. There was no outside, no other, no beyond the universe in any meaningful sense. To ask whether there were other universes was like asking whether there were colors beyond the visible spectrum or sounds beyond the range of hearing. The answer might be yes, but the question itself strained the boundaries of what the words were designed to contain. But physics, in the last few decades of the 20th century and the first decades of the 21st, has moved in a remarkable direction. Slowly, carefully, through through the accumulated weight of theoretical work that followed unavoidably from ideas that were initially proposed for entirely different reasons, physicists have found themselves confronting the possibility that our universe is not alone, that it is one bubble in an inconceivably vast and perhaps infinite sea of bubbles, each one a separate universe with its own laws, its own physical constants, its own history, its own particular way of being real. This is the multiverse. And to understand how physicists arrived at this idea, and why it is not merely idle speculation but a consequence of some of the best established physics we have, we need to return to inflation. Recall that inflation was proposed to solve the horizon problem, and that it proposes a period of extraordinarily rapid exponential expansion in the very earliest moments of the universe's history. One of the features of most inflationary models is that this rapid expansion is driven by a field called the inflatant field that has a high energy state and wants to decay to a lower energy state. The inflatant field is like a ball balanced at the top of a hill. It is in an unstable high-energy configuration, and it will eventually roll down to a more stable lower-energy state, releasing its energy as it does so. This release of energy is what ends inflation and produces the hot, dense state that we call the Big Bang, the beginning of the universe as we know it. But here is the crucial point. In most versions of inflation, the inflatant field does not decay everywhere at once. It decays in patches. In some regions of the inflating space, the field tunnels or rolls to its lower energy state, ending inflation locally and creating a hot, dense region that evolves into a universe like ours. But in the regions surrounding those patches, inflation continues. The surrounding inflating space keeps expanding exponentially, faster than the speed of light, faster than any signal can travel through it. This creates a situation where the inflating space as a whole never stops expanding. Every time inflation ends in one region, creating a pocket of non-inflating space, a bubble universe, the surrounding inflating space has expanded so much that there is vastly more inflating space than before. More regions in which inflation can end, more bubble universes can form. The process continues indefinitely, producing an infinite number of bubble universes, each one isolated from the others by the exponentially expanding inflating space between them. This is called eternal inflation. And it is not a fringe idea. It is a consequence of some of the most carefully developed and observationally supported inflationary models. If inflation happened, and the evidence strongly suggests it did, then eternal inflation is the likely consequence, and an infinite sea of bubble universes is the likely result. Each bubble universe in this picture is a complete, self-contained cosmos. It has its own Big Bang, its own hot, dense beginning, its own cooling and expansion, its own potential for structure formation and star formation and perhaps life. It may have different physical constants from ours, different values of the fundamental parameters that govern the behavior of matter and energy, if the inflatant field decays to a different configuration in different bubbles. It may be radically different from our universe, or it may be remarkably similar, depending on the details of the inflationary model. From the outside of a bubble universe, if outside even means anything in this context, the bubble would look like a small region of non-inflating space surrounded by a vast, rapidly expanding inflating medium. Like a soap bubble in a foam that is itself expanding so fast that new soap bubbles form continuously throughout its volume. An endless, ever-expanding foam of universes, each one complete in itself, each one separated from the others by exponentially expanding space that can never be crossed. In this picture, our universe is one of those bubbles. Our Big Bang was the moment when the inflatant field in our particular region of the inflating space decayed to its lower energy state, releasing the energy that became everything we know. Our universe is not infinite. It is not all there is. It is one bubble in an infinite foam, surrounded by inflating space and by other bubbles, each one a universe in its own right. This is a staggering idea, and one of its most important properties is that the bubbles are, in principle, unable to communicate with each other. The inflating space between them expands faster than any signal can cross it. A photon emitted from one bubble universe, aimed at another bubble universe, would never arrive because the distance it had to cross would grow faster than it could travel. The bubbles are forever isolated from each other. We can never see another bubble universe. We can never send a signal to one or receive a signal from one. Or so the simplest version of the story goes. Because there is one way that bubble universes can interact with each other. One way that the isolation can be broken, that the wall between bubbles can be breached, that two separate universes can leave marks on each other. They can collide. Breathe. The foam of universes is real, at least theoretically. The bubbles are forming, endlessly, throughout the inflating space. And the bubbles can collide. Rest in that. Let the idea settle. The multiverse is not an empty speculation. It is a consequence of the physics we have the best evidence for, and it has consequences that can, in principle, be tested. Consequences that may already be visible in the oldest light in our universe. In the cold spot, when two soap bubbles touch, something remarkable happens. They do not simply pass through each other, and they do not immediately merge into one larger bubble. Instead, at the point of contact, they share a wall. A thin, curved membrane forms between them, a boundary that belongs to both bubbles simultaneously, a place that is neither one bubble nor the other, but the meeting point of two separate enclosed spaces. The bubbles deform slightly at the contact point. Their spherical shapes are disturbed. The place where they touched carries the memory of the collision in the changed geometry of both surfaces. Now imagine that instead of soap bubbles in air, you are thinking about bubble universes in the inflating space of the eternal multiverse. Universes that formed independently in separate regions of the exponentially expanding inflating medium, each one containing its own Big Bang, its own physics, its own history. And imagine that two of these bubble universes, expanding outward through the inflating space, reach the point where their boundaries meet. What happens? This question was examined carefully by physicists including Matthew Johnson, Eridanus, and their collaborators in a series of papers beginning around 2010. Their work attempted to calculate, using the best available theoretical tools, what the collision between two bubble universes would look like from inside one of the colliding bubbles. What signature would such a collision leave in the observable universe of the bubble that survived the encounter? The calculation is deeply complex and involves general relativity, quantum field theory, and the geometry of space-time in ways that require considerable mathematical machinery to handle properly. But the broad physical picture that emerges from this work is comprehensible, and it is extraordinary. When two bubble universes collide, the collision does not destroy either bubble. It is not like two soap bubbles merging into one. The bubbles are regions of non-inflating space surrounded by inflating space, and their collision is a geometric event in the space-time of the multiverse that has specific, calculable consequences for the physics inside each bubble. From inside our bubble, from inside our universe, the collision would appear as a disturbance propagating inward from the point of contact. A ripple in the fabric of space-time, spreading from the collision boundary into our universe at the speed of light. This disturbance would have been moving through our universe since the very earliest moments after our Big Bang, since before the first stars, before the first atoms, before even the first nuclei formed. It would have traveled outward from one point on the boundary of our universe, spreading like a growing sphere of disturbed space-time through everything our universe contained. And when this disturbance passed through the region of space that later became the surface of last scattering, the shell from which the cosmic microwave background was emitted, it would have left a mark. A circular region where the temperature of the CMB was different from the surrounding areas. A disk on the sky where the ancient light tells a slightly different story from the light around it. The shape of this mark is crucial, because the disturbance propagates as a sphere expanding from a point, and the surface of last scattering is itself a sphere surrounding us from all directions. The intersection of these two spheres is a circle. The mark of a bubble universe collision in the CMB would be circular, a circular region with a different temperature from its surroundings. And the temperature profile within that circle would have a specific, predicted shape. Not a uniform disk of cold or hot temperature, but a gradient, a smooth variation from the center to the edges. And depending on the details of the collision, the profile could include a cold central region surrounded by a ring of slightly different temperature, a nested, concentric structure. This predicted profile has a name in the technical literature. It is sometimes called the disk-like structure with a circular boundary and a specific temperature gradient, and the precise shape depends on the energy of the collision and the properties of the colliding bubbles. But the general features are consistent across different models. A circular, disk-shaped feature in the CMB, with a temperature profile that varies smoothly from center to edge. Now recall the cold spot. A cold region in the CMB, roughly circular in shape, several degrees across, with a temperature deficit of roughly 70 to 80 microkelvin at its center, and with an observed temperature profile that has been described as having a cold central region surrounded by a ring of slightly warmer temperatures, a concentric, nested structure. The match is not perfect. No prediction in a theory this complex and this difficult to calculate is ever perfectly matched by an observation. But the qualitative agreement between what a bubble universe collision is predicted to produce and what the cold spot actually looks like is striking enough to deserve serious attention. It is striking enough that it has motivated a dedicated research program, a sustained effort by physicists to determine whether the cold spot could genuinely be the signature of a collision between our universe and another bubble universe billions of years ago. If it is, then the cold spot is not just an anomaly in the CMB. It is a message, a physical record of the most extraordinary event in the history of our universe. A bruise left by the impact of a neighbor we will never see, from a universe that exists alongside ours in the vast, eternal, exponentially expanding foam of the multiverse. The cosmic bruise. The mark left in the oldest light by the only kind of contact that two bubble universes can ever have with each other. Not communication, not exchange, not any kind of ongoing relationship, but a single, violent, ancient impact. A moment of contact at the very beginning of our universe's history, when our bubble and a neighboring bubble briefly touched, and in that touching, left each other forever changed. Think about what it would mean to find such a bruise. Not just to speculate about it, not just to calculate what it might look like, but to actually find it, to measure it, to confirm that the circular cold region in the direction of Eridanus is genuinely, verifiably, the impact scar of a collision with another universe. It would mean that we are not alone. Not in the sense of life on other planets, though that question remains open and fascinating, but alone in a deeper sense. Alone as a universe. Alone as a region of space and time. A single bubble of existence in an otherwise inflating void. We would not be alone in that sense. We would have a neighbor. We would have evidence of a neighbor. We would be holding, in the maps of our oldest light, the fingerprint of another universe. The multiverse fingerprint. written in the ancient scar of the cold spot, if the Bruise Theory is correct, written in light that has been traveling for nearly 14 billion years, written in the baby picture of our universe, in the place where the image is cold and strange and refuses to be explained away. This is the most extraordinary possibility that the cold spot presents. Not the only possibility, not the proven explanation, but the possibility that sits at the end of the chain of reasoning that begins with the anomaly in the CMB and follows the physics as far as it will go. The collision happened, if it happened, long before any of this. Long before the Milky Way, long before the sun, long before the earth, long before the first living thing drew breath and looked up at the sky. It happened in the first fraction of a second of our universe's existence, when our bubble of non-inflating space first touched the bubble of another universe, and the two great structures of space-time brushed against each other in the inflating void. And the mark of that touch is still here, still visible, still cold, still sitting in the oldest light, in the direction of the river constellation Eridanus in the southern sky. The ancient scar, the cosmic bruise, the multiverse fingerprint. Breathe. Feel the weight of it. Not the weight of certainty, because this is not certainty, but the weight of genuine, serious, physically motivated possibility. The weight of an idea that follows from established physics, that makes specific predictions, that matches qualitative features of a real observation. Rest in the collision. Something touched us, once, at the very beginning, and it left a mark. There is a moment in every great scientific story when the pieces begin to come together. When the anomaly and the theory and the observation align in a way that is not yet proof, but is more than coincidence, more than speculation, more than the idle dreaming of scientists who wish the universe were more interesting than it is. A moment when you can see, clearly and with a feeling that is something between intellectual excitement and genuine awe, how the strange fact and the strange theory fit each other, how the shape of one matches the shape of the other, how the universe might be offering you a glimpse of something true. The Bruise Theory is in that moment. It has been in that moment for several years now, tantalizingly unresolved, neither confirmed nor refuted, neither proven real nor explained away, sitting in the space between certainty and possibility that is where the most important scientific questions always live for a time before the evidence finally speaks definitively. Let us trace the argument carefully, following it from its beginning to its present state, because the path it takes is itself worth understanding. It begins with inflation. Inflation, as we have discussed, is the theory that the universe underwent a period of exponentially rapid expansion in its earliest moments, and the evidence for inflation is substantial. The pattern of temperature fluctuations in the CMB is consistent with inflationary predictions. The geometry of the universe, which appears to be flat rather than curved, is consistent with inflationary predictions. The large-scale structure of galaxies and clusters is consistent with what inflation, followed by billions of years of gravitational collapse, would produce. Inflation is not proven with the certainty of a mathematical theorem, but it is supported by the best cosmological data we have. If inflation happened, then eternal inflation is likely. The physics of most inflationary models implies that once inflation starts, it continues indefinitely in the regions surrounding any bubble of non-inflating space. New bubbles form constantly. Old bubbles expand. The inflating space between them grows exponentially. The multiverse, the vast eternal foam of bubble universes, is a robust prediction of inflationary cosmology. It is not a fringe idea or a philosopher's speculation. It is what the physics says should happen if inflation is real. If the multiverse exists, then bubble collisions can occur. The bubble universes in the eternal inflationary multiverse are not infinitely far from each other. They form at various locations in the inflating space, and they expand outward through that space. Depending on the relative positions of two bubbles when they form and the rate at which they expand, some bubbles will be close enough together to collide before the expanding inflating space between them separates them beyond reach. The probability of any given bubble universe having experienced a collision is uncertain. It depends on the details of the inflationary model, on how densely packed the bubble nucleation events are, on how fast the bubbles expand. In some models, collisions are common. In others, they are rare. We do not know which type of model describes our universe, but the possibility of collision is real, and the consequences of collision are calculable. If our universe collided with another bubble universe early in its history, the collision would have left a specific signature in the CMB. The work of Johnson, Pyrrhus, and their collaborators defined what that signature should look like. It should be a circular region on the CMB sky, with a temperature profile that varies smoothly from center to edge, potentially including a cold central region with a surrounding ring of different temperature. The exact profile depends on the details of the collision, particularly on the relative energy densities of the two colliding bubbles and the angle at which they met. When researchers compared this predicted signature with the observed properties of the cold spot, they found a remarkable qualitative match. The cold spot is approximately circular. It has a cold central region. It has been described as having a concentric structure with the coldest temperatures at the center surrounded by a region of slightly warmer temperatures, surrounded in turn by a broader cold region. This nested, circular, cold structure is precisely the kind of thing that a bubble universe collision is predicted to produce. Furthermore, the size of the cold spot, several degrees across on the sky, is consistent with what you would expect from a collision that occurred very early in the universe's history. A collision that happened at the very beginning of our Big Bang would have had time to send its disturbing ripple across a significant fraction of the observable universe before the surface of last scattering was formed. The intersection of that ripple with the surface of last scattering would produce a circle of precisely the angular size we observe. The quantitative match is harder to assess. Getting the precise temperature depth of the cold spot, its exact profile, the precise combination of its size and coldness, to match the predictions of a specific collision model requires more detailed calculation and more constrained observations than are currently available. The Planck data has given us the best measurements yet of the cold spot's properties, but those measurements still carry uncertainties, and the theoretical predictions carry their own uncertainties from the unknown details of the inflationary model and the collision geometry. But the story does not end with the CMB. If the Bruise theory is correct, if the cold spot is genuinely the signature of a bubble universe collision, then the collision should have left other marks as well. The disturbance that produced the cold region in the CMB would also have affected the large-scale structure of matter in the universe in the region downstream from the collision. The distribution of galaxies in the direction of the cold spot might be different from what you would expect if there had been no collision. And this is where the supervoid enters the story in a new light. Because if the collision produced a disturbance in the fabric of space-time that passed through the region of our universe corresponding to the direction of the cold spot, that disturbance might also have affected the growth of large-scale structure in that region, potentially producing the anomalously empty region that we observe as the Eridanus supervoid. In this picture, the supervoid is not an independent explanation for the cold spot. It is part of the same story. The collision produced both the cold region in the CMB and the empty region in the large-scale structure, two different imprints of the same ancient impact, seen in two different ways. The CMB tells us about the conditions at the surface of last scattering 380,000 years after the Big Bang. The supervoid tells us about the large-scale structure as it exists today, nearly 14 billion years later. Both are fingerprints of the same event. Both are marks left by the cosmic bruise. This is an elegant and compelling narrative. It takes two puzzling anomalies, the cold spot in the CMB and the Eridanus supervoid, and proposes that they are manifestations of a single underlying cause. A bubble universe collision billions of years ago that left its mark in both the ancient light and the modern structure of our universe. The Bruise Theory is not proven. Let us be clear and honest about that. It is a serious, physically motivated hypothesis that is consistent with observations and that makes testable predictions, but it has not been tested definitively. The existing data is consistent with the Bruise Theory, but it is also, to varying degrees, consistent with other explanations. More data, sharper instruments, better theoretical predictions will be needed to determine whether the cold spot is genuinely a cosmic bruise or whether it can be explained by more ordinary physics. But the Bruise Theory is alive. It has not been ruled out. It has not been shown to be inconsistent with any robust observational fact. And it remains, for many physicists who think about these questions seriously, the most extraordinary and the most intellectually compelling hypothesis for what the cold spot might be. If it is right, then we are looking at the most important discovery in human history. Not the discovery of a distant galaxy, not the detection of gravitational waves, not the imaging of a black hole, though all of those things are magnificent, but the discovery of evidence that our universe is not alone, that there are others, that the multiverse is real, that the eternal inflationary foam of bubble universes is not merely a theoretical consequence of inflation, but a physical reality with observable consequences. The cosmic bruise would be the multiverse fingerprint, the mark left in our universe by the only touch that two bubble universes will ever share. Brief. The Bruise Theory is there, waiting. The cold spot is there, waiting. And the universe, vast and patient and full of secrets it has not yet revealed, is waiting too. Rest in the possibility. It is enough, for now, to understand that the possibility is real, that the physics supports it, that the observation is consistent with it. To feel the weight of what it would mean, and to rest, gently, beneath the sky that contains it. To understand what it would mean to confirm the Bruise Theory, to truly feel the weight of what the cold spot might be telling us. It helps to step back from the technical details, from the statistics and the temperature profiles and the angular sizes, and to sit for a moment with the philosophical enormity of the idea. What is a fingerprint? A fingerprint is a mark left by contact, a record of a touch. When you press your finger against a surface and leave behind the whirled impression of your skin, you are leaving evidence of a moment of contact, a record that you were there, that something happened at that surface at that time. The fingerprint is not the finger. It is the mark the finger left. And from the mark alone, if you know enough about how fingerprints are made and what they look like, you can infer the existence of the finger, the hand, the person, even though none of those things may be visible now. The multiverse fingerprint works the same way. If the cold spot is a bubble universe bruise, then it is not the other universe. It is the mark the other universe left. The other universe is gone, in any practical sense, separated from us by expanding, inflating space that will never allow any further contact between us. But the mark of its touch, the impression left in the first light of our universe by the disturbance of its collision, is here. It is in our sky. It is in our CMB maps. It is visible, if you know how to look for it and what to look for. From this mark, if the Bruise Theory is correct, we can infer the existence of the other universe. Not see it, not communicate with it, not know anything about its contents or its laws or its history, but infer its existence. Establish that it was there, that it touched us, that in the first fraction of a second of our universe's history, our bubble of space-time and its bubble of space-time briefly shared a boundary. And in that sharing, exchanged a disturbance that propagated through our universe and eventually became the cold spot we observe today. This would be the most extraordinary piece of indirect evidence in the history of science. Extraordinary not because it would be the first time scientists have inferred the existence of something they cannot directly observe. Science does this routinely. We infer the existence of black holes from the behavior of matter and light around them. We infer the existence of dark matter from its gravitational effects on visible matter. We infer the existence of neutrinos from energy conservation in nuclear reactions. Indirect inference is a fundamental tool of science, and when it is done carefully and with appropriate rigor, it is just as valid as direct observation. But the inference of another universe would be different in kind from any of these. Because all of those other inferences, the black holes, the dark matter, the neutrinos, are inferences about things that exist within our universe. They are parts of our cosmos, subject to the same laws, residing in the same space-time, in principle reachable by light or by influence. Another bubble universe is different. It is not part of our universe. It is not subject to the same laws, at least not necessarily. It does not reside in our space-time. It cannot be reached by any signal. To infer its existence from the cold spot would be to step outside our universe in the only way that physics might ever allow us to do so. Not physically, not with any instrument or probe or signal that we can send, but intellectually, through the careful analysis of a mark left in our oldest light. We would be reasoning about something that exists beyond our universe on the basis of evidence left inside our universe, in the same way that a forensic scientist reasons about a crime that happened in the past from traces it left in the present. The multiverse fingerprint would transform cosmology. It would transform it from a science about one universe, our universe, into a science about a vastly larger reality of which our universe is one tiny part. It would change our understanding of why the universe has the properties it has, because in an eternal inflationary multiverse, different bubble universes can have different physical constants, and the fact that we live in a universe with constants hospitable to life would be explained not by special design, but by the simple fact that we can only exist in a universe where we can exist. Other constants are possible, realized in other bubbles. We are here because our bubble happened to have the right ones. It would change our understanding of the beginning. Our Big Bang would no longer be the absolute beginning of everything, but only the beginning of our bubble, the moment when the inflating field in our particular region of the eternal inflating space decayed and released its energy. Before our Big Bang, the inflating space had already existed, and other bubbles had already formed, and some of them had already collided with each other. And some of those collisions had produced bruises in other CMB maps that observers in those other universes might someday discover, if they exist and if they look. It would change our understanding of our place. We are already accustomed to a sequence of discoveries that have displaced human beings from the center of things. We discovered that the Earth is not the center of the solar system. We discovered that the Sun is not the center of the galaxy. We discovered that the Milky Way is not the center of the universe, that there is no center of the universe in any meaningful sense. And we discovered that the observable universe, vast as it is only a fraction of the larger universe that lies beyond our horizon. The multiverse takes this displacement one step further. Not just our planet, not just our star, not just our galaxy, not just our universe, but even our universe is one among countless others. We are a bubble in a foam, one island in an archipelago so vast that the word archipelago no longer captures it. One story in a library that may be infinite. And yet, within all of that vast, incomprehensible multiplicity, the mark is here. In our CMB, in our sky, in the direction of Eridanus, cold and circular and persistent, the possible fingerprint of the one moment of contact we ever had with any of our countless neighboring universes. The one time, at the very beginning, when another universe touched us and left a bruise. There is something deeply moving about this, if you let yourself feel it. Not frightening, not diminishing, but moving, in the way that any recognition of connection is moving, even when the connection is indirect, even when what you are connected to is unreachable and perhaps utterly different from you. We are not entirely alone, even in the multiverse. Something else touched us. Something else left a mark in our oldest light. The multiverse fingerprint is there. Perhaps, if the Bruise Theory is correct, if the cold spot is what the most extraordinary hypothesis says it is, and we are looking at it, right now, tonight, with the maps produced by the most sensitive instruments humanity has ever built, we are looking at the oldest light in the universe and reading in it the possible signature of another universe's touch. Breathe. Feel the connection. The universe is vast, and it may not be alone, and in its oldest light there is a mark that may be the proof. Rest in that possibility. It is enough. There is a kind of honesty that science demands, and it is not always comfortable. It is the honesty of saying, clearly and without evasion, that we do not know, that the evidence is insufficient, that the hypothesis, however beautiful, however physically motivated, however consistent with what we observe, has not yet been confirmed and may never be confirmed and might ultimately be wrong. This honesty is not weakness. It is the thing that makes science trustworthy, the thing that distinguishes it from other ways of claiming knowledge, the thing that allows it to accumulate genuine understanding over time rather than simply accumulating assertions. A science that cannot say, "I do not know," is not a science. It is a belief system, and the willingness to live with uncertainty, to hold a beautiful idea loosely because the evidence has not yet fully supported it, is one of the most important virtues that science has developed. So let us be honest about the cold spot and the Bruise Theory. We do not know that the cold spot is a bubble universe bruise. We know that the cold spot is real, that it is a genuine anomaly in the CMB, that it has been confirmed by multiple independent instruments, and that its probability of being a random fluctuation in the standard inflationary model is low enough to merit a physical explanation. We know that the supervoid hypothesis explains some, but probably not all of the cold spot's temperature deficit. We know that the Bruise Theory makes predictions that are qualitatively consistent with what we observe. But we do not know that the Bruise Theory is right. The gap between qualitative consistency and confirmed truth is large. Many theories have been qualitatively consistent with some observations only to fail when the observations became more precise or when additional tests were applied. The history of science is full of beautiful, physically motivated ideas that turned out to be wrong, ideas that matched the available data well, but that were ultimately inconsistent with the fuller picture that emerged as understanding deepened. For the Bruise Theory to be confirmed, several things would need to happen. The temperature profile of the cold spot would need to be measured with enough precision to rule out alternative explanations and to match the specific predictions of bubble collision models, not just qualitatively, but quantitatively. The polarization of the CMB in the cold spot region would need to be measured and compared with predictions. The large-scale structure in the direction of the cold spot would need to be mapped in much greater detail to determine precisely the properties of the Eridanus supervoid and whether they are consistent with what a collision would produce. And there is a deeper problem. Even if all of these measurements came back consistent with the Bruise Theory, that would not constitute absolute proof. Consistency is not the same as uniqueness. A measurement that is consistent with one hypothesis may also be consistent with other hypotheses that have not yet been formulated. The history of physics is full of cases where apparently conclusive evidence for one theory turned out to be equally consistent with a different theory that explained the same observations in a completely different way. There is also the problem of what physicists call the measure problem in eternal inflation. The multiverse, if it exists, contains an infinite number of bubble universes. In an infinite collection, almost any configuration is possible, and almost any configuration will occur an infinite number of times. This makes it difficult to calculate probabilities in the multiverse in a meaningful way. If there are infinitely many universes with cold spots caused by collisions and infinitely many universes with cold spots caused by other mechanisms, what does it mean to say that the collision explanation is more probable? The measure problem is one of the deepest unsolved problems in inflationary cosmology. It prevents us from making precise quantitative predictions about what we should observe in our universe if eternal inflation is real, which in turn prevents us from definitively testing the Bruise Theory against its competitors. This is not a reason to dismiss the Bruise Theory. It is a reason to continue working on the theoretical foundations that would make the predictions sharper and the tests more definitive. There is also the question of the limits of observation. We live in a universe with a finite observable region, bounded by the horizon defined by the age of the cosmos and the speed of light. The surface of last scattering, from which the CMB was emitted, is near the edge of that observable region. To test the Bruise Theory fully, we would ideally want to observe the large-scale structure and the CMB at multiple scales and multiple frequencies with instruments far more sensitive than those we have today. Some of those observations may be technically possible in the future. Others may be fundamentally impossible, beyond the reach of any instrument we could ever build, because the information we need simply does not exist in the light that has reached us. The universe keeps some of its secrets permanently. The horizon that limits our sight is not just a technological challenge. It is a fundamental physical limit, a boundary imposed by the finite age of the cosmos and the finite speed of light. Beyond that boundary, the universe exists and has its history, but its light has not arrived, and its secrets have not been shared. And yet the honest uncertainty about the Bruise Theory is not despair. It is not a reason to dismiss the cold spot as unimportant or the multiverse as idle speculation, because the uncertainty is the space in which science lives. The questions that have not yet been answered are the ones that drive the instruments and the missions and the careers and the long nights of careful analysis that advance our understanding. The cold spot is real. It is anomalous. It demands explanation. And among the explanations that have been seriously proposed, the Bruise Theory is the most extraordinary, the most far-reaching in its implications, and the most beautiful in its way of connecting a tiny cold region in the oldest light to the vastest possible context, the entire multiverse. Perhaps the cold spot will eventually be explained by something more ordinary, some subtlety in the foreground removal, some statistical fluke that was less improbable than it appeared, some refinement of the supervoid hypothesis that finally makes the numbers work. Perhaps, but until that explanation arrives, and it has not arrived yet, the Bruise Theory remains in play. It remains a serious possibility, supported by real physics, consistent with real observations, making real predictions that can in principle be tested. The ancient scar is there. The impossible chill is there. The cosmic bruise is there, at least as a possibility. And the question of what made it remains open. An open question is not a failure. An open question is an invitation. An invitation to look more carefully, measure more precisely, think more deeply, and remain alert to the possibility that the universe is stranger and richer and more extraordinary than our current understanding can contain. The cold spot is that invitation. Cold and circular and patient in the direction of Eridanus, in the oldest light in existence. Waiting for the answer that has not yet arrived. Waiting, if the Bruise Theory is right, to tell us that we are not alone in the deepest sense of the word. Breathe. The uncertainty is not emptiness. It is space. Space in which truth is still being found. Space in which the universe is still being understood. Rest in the open question. It is comfortable here, in the not yet known. The stars are still above you. The ancient light is still arriving. And the cold spot is still there, cold and patient, carrying whatever secret it contains. Come back now, gently, to where we began. To the cool ground beneath you, and the clear air around you, and the open sky above, scattered with stars that are each a sun and each a story, and each a point of ancient light that has crossed unimaginable distances to arrive at your eye at this particular moment. Come back to the quiet. Come back to the breathing. Come back to the feeling of being a small, temporary, conscious arrangement of atoms lying on a small planet, looking up at a cosmos so vast. You have traveled a long way tonight. In the way that the imagination can travel, which is the only way that any of us will ever cross the distances involved, you have gone from the stars above your head to the edge of the observable universe. You have followed the light backward in time to the moment when the universe first became transparent. You have seen the baby picture of everything, the almost perfect map of the infant cosmos with its tiny, barely perceptible fluctuations that are the seeds of all structure. You have found the ancient scar, the impossible chill, the cold spot in the direction of Eridanus, and you have sat with it long enough to understand why it is strange and why it matters and why it has been quietly astonishing the people who study it for decades. And you have heard the most extraordinary hypothesis, the Bruise Theory, the idea that the cold spot is not a fluke or a foreground artifact or the imprint of a nearby void, but a cosmic bruise. The mark left in our oldest light by the impact of a collision between our universe and another bubble universe, a neighboring island of space-time in the eternal inflationary foam of the multiverse. A fingerprint pressed into the first light by the only touch that two universes in the multiverse can ever share. You know now that this hypothesis is not proven. You know that it is a serious physical possibility, supported by well-established theory, consistent with observation, making predictions that can in principle be tested, but not yet confirmed and perhaps not confirmable with the instruments we have today. The uncertainty is real, and the honesty of that uncertainty is important. Science does not pretend to know what it does not know. But here is the thing about the Bruise Theory, the thing that stays with you after the technical details have faded, the thing that belongs to the domain not of equations, but of meaning. Even as a possibility, it changes the way the sky feels. When you lie beneath the stars and look up now, you are not just looking at points of ancient light in a familiar and finite cosmos. You are looking at the sky of a universe that may have bumped into another universe when it was very young. A universe that may carry, in its oldest light, a record of that contact. A universe that is not, if the Bruise Theory is right, entirely alone in the deepest sense. The cold spot, that cold circular region in the direction of the river constellation, is always there above you. You cannot see it with your naked eye. It is written in frequencies that your eyes cannot detect. But it is there, as real as any star, as permanent as any feature of the ancient light, cold and circular and patient in the sky you are lying beneath. There is something deeply comforting about that, once you let yourself feel it. Not because a collision with another universe is a gentle thing, not because the cosmic bruise is a friendly mark, but because it is a mark of contact. It is evidence that the universe we live in is not sealed off, is not utterly isolated. is not the only thing there is, even at the largest possible scale. Something else is out there, perhaps infinitely many something elses. And one of them, a very long time ago, reached out and touched us. We did not know about it for billions of years. For all of human history until the last few decades, we did not even know the oldest light existed, let alone that it carried an anomaly. For most of those few decades, the anomaly was a puzzle without a clear solution. And now here we are. In a time when the instruments have been built and the theories have been developed and the question has been asked clearly enough that the possibility of an answer exists. We are the first generation of human beings to have this question on the table, to be living in the time when the Bruise Theory is a serious scientific hypothesis. That is remarkable. You are here, in this moment, in this narrow window of cosmic history, when the universe is transparent enough and the instruments are sensitive enough and the theories are developed enough that the possibility of finding the fingerprint of another universe in our oldest light is a real scientific project with real scientific papers being written about it and real scientific debates being had about it. Earlier generations did not have this possibility. Future generations may have the answer, but you are here in the moment when the question is fully alive, when the possibility is real, when the universe is still holding its secret and scientists are still reaching for it. There is something beautiful about living in the question, not just in the answer. The question itself, this question, the question of whether the cold spot is a cosmic bruise, whether the multiverse is real, whether the fingerprint of another universe is hidden in our oldest light, is one of the most extraordinary questions ever formulated by a human mind. It is a question that takes everything we know about physics and inflation and the CMB and the structure of space-time and asks, is all of this part of something even larger? Is our universe one story in an infinite library? Is the scar in the oldest light the proof? We do not know yet. And in the not yet knowing, there is a particular kind of peace. The peace of living in a universe that still has secrets. The peace of knowing that the story is not finished. That the maps are still being made, the instruments are still being built, the data is still being analyzed, the questions are still being asked. The peace of being part of a species that cannot stop reaching outward, cannot stop asking what is there, cannot stop following the light to whatever it leads. The cold spot will be there tomorrow night. And the night after. It has been there since before the first star, and it will be there long after the last, carrying its impossible chill in the oldest light, in the direction of the river in the southern sky, patient and cold and circular and strange. Waiting, as it has always waited, for the understanding that is still being built, one careful measurement at a time, one careful calculation at a time, one careful paper at a time, by the patient and determined and endlessly curious people who have devoted their working lives to reading the universe's baby picture correctly. And you are here, lying beneath the stars, breathing slowly, feeling the weight of the night around you. The imaginary ground is cool and firm beneath you. The imaginary stars are countless above you. And somewhere in the sky, in a direction you could point to now if you had a map of the CMB, in the part of the southern sky where the river constellation wins its imaginary way through the darkness, there is a region of the oldest light that is cold. Colder than everything around it. Larger than it should be. Circular and persistent and real. The ancient scar. The cosmic bruise. The impossible chill. The multiverse fingerprint. If the most extraordinary hypothesis is correct, it is there right now, above you. As it was above the people who first looked at the WMAP maps and noticed something strange. As it was above the generations before us who looked at the same sky and saw only stars and could not have imagined that the oldest light carried a wound. As it will be above whoever comes after us, whether they have found the answer or are still reaching for it. The universe keeps its baby picture. And in the baby picture, there is a mark. And in the mark, there may be a story about the most extraordinary thing that has ever happened to our universe. A moment of contact, billions of years ago, when another universe reached across the eternal inflating void and touched us, just once, and left the only mark that two universes in the multiverse will ever share. Breathe. Let the sky hold you. Let the ancient light surround you, everywhere, from every direction, carrying its oldest memory. You are lying beneath a universe that may not be alone, that may have a neighbor or many neighbors, stretching away through the inflating foam of the eternal multiverse in directions that no light will ever cross, in spaces that no signal will ever bridge, in realities that we will never see or touch or know except through this one cold mark in the oldest light we have. That is enough. The mark is enough. The question is enough. The possibility, held gently and honestly, and with the appropriate humility of science, is enough to make the night sky something more than it was before you heard this story. Something larger, something more connected, something that carries, in its cold and ancient and everywhere glow, the faintest possible whisper of a hello from somewhere unimaginably far away. The scar is there. The sky is there. You are there, beneath it, breathing. And the universe, vast and patient, and perhaps not entirely alone, is turning slowly above you in the dark. Rest now. Let the cold spot be cold. Let the ancient light be ancient. Let the questions be questions, and the possibilities be possibilities, and the night be the night, deep and quiet, and full of a darkness that is not empty, but alive with the oldest light and the oldest secrets and the most extraordinary possibilities that a conscious mind has ever had the privilege of contemplating. You have traveled to the edge of everything tonight, to the bruise at the edge of everything, and now you are coming back, slowly, gently, the way you return from any great distance, with the feeling that you have seen something worth seeing and that the ordinary world you are returning to is, because of what you have seen, a little larger than it was before. The stars are above you. The ancient light is everywhere. The cold spot is there, in the direction of the river, cold and circular and patient. And you are here, small and temporary and conscious and full of wonder. Sleep now. Let the universe continue without your watching it. It will be there in the morning, vast and strange and beautiful. The ancient scar will still be cold. The first light will still be everywhere. The question will still be open. And tomorrow night, if you look up at the sky and feel it differently than you did before, if the darkness between the stars seems somehow richer, somehow more populated with possibility, somehow more connected to you and you to it, then this long, slow journey through the oldest light has done what it set out to do. It has made the cosmos feel like home. Not a small home, not a safe home, but a home. A vast and ancient and perhaps infinite home, in which your universe is one bubble, and your galaxy is one island, and your star is one sun, and your life is one brief and precious flickering of consciousness in a cosmos that may contain more life, more consciousness, more stories than any number we have yet invented could describe. The bruise at the edge of everything is there. It has always been there, and now you know it. Good night. There is something that deserves more attention before we move on from the maps and the instruments and the careful cartography of the ancient light. It is the question of what it actually means to make a map of something so vast and so old, and what it costs, in human terms, to build the instruments required to read it. The COBE satellite, the first instrument to map the cosmic microwave background across the full sky with enough sensitivity to detect the temperature fluctuations, was the product of more than 2 decades of planning, development, and advocacy. Its principal investigators spent years arguing for its importance. Years convincing funding agencies that a satellite designed to measure temperature differences of 100,000th of a degree in the oldest light in the universe was worth the investment of time and money and engineering effort that it required. This is not unusual in science. The most important experiments are often also the most difficult to justify in advance, because their importance depends on what they find, and what they find is unknown until they have been built and launched and operated. You cannot promise a discovery. You can only promise a measurement, and hope that the measurement reveals something worth the effort. The COPE team promised a measurement, and what they found, the modeled, barely perceptible pattern of temperature fluctuations in the ancient light, was worth far more than the effort. It was, as George Smoot described it, the imprint of tiny ripples in the fabric of space-time set in place by the birth pangs of the universe. It was the first direct image of the seeds of all structure, the first glimpse of the conditions from which everything we see today eventually grew. WMAP and Planck followed the same path. Years of planning, years of development, years of argument and advocacy and engineering and testing, all in pursuit of a sharper image of the same ancient light. Each mission justified by the promise of better measurements, finer resolution, more precise determination of the parameters that describe the universe. Each mission delivering on that promise and revealing, with increasing clarity, both the beauty of the standard model and the stubborn persistence of the anomalies that do not fit it. The cold spot was seen by COPE dimly. It was seen more clearly by WMAP. It was seen most clearly of all by Planck. Each sharper instrument not erasing it but confirming it, not explaining it away but delineating it more precisely, giving it sharper edges and more precise measurements of its temperature and extent. Each new map saying, more clearly than the last, this is real. This is not noise. This is not a mistake. This is something that exists in the ancient light, and it deserves an explanation. The maps of the infant universe are some of the most extraordinary documents ever produced by human beings. Not because they are beautiful, though they are beautiful in their way, in the abstract visual language of color-coded temperature scales and false color representations of a sky our eyes cannot see, but because of what they represent. They are the record of decades of work by hundreds of scientists and engineers and technicians, all devoted to the single goal of reading the universe's oldest message more clearly. And in that message, there is a cold spot, an anomaly, a mark that should not be there. And the question of what made it is still, as of this night, as of this moment, unanswered. That unanswered question is the inheritance of every new generation of cosmologists. It is passed down with the maps, with the data, with the careful statistical analyses and the theoretical papers, and the ongoing debates about what the cold spot means and what could have made it. It is the outstanding item on the agenda of the science that is trying to understand where everything came from. And it may be the most important item. Brief. The maps are there. The anomaly is there. The question is alive. Before we leave the cold spot as a simple observational fact and move into the territory of explanations and hypotheses, it is worth spending a little more time with the cold itself, with the feeling of what it means for a region of the oldest light to be cold in the way the cold spot is cold. Temperature in the cosmic microwave background is not like temperature in a room. When we say a room is cold, we mean it contains less thermal energy than a comfortable room, that the molecules of air are moving more slowly, that the heat that radiates from warm objects is not enough to overcome the rate at which it is being lost to the cooler surroundings. Cold, in everyday life, is a felt experience. It is something the body knows. It is something that makes you reach for a blanket or move closer to a fire. Cold in the CMB is a different kind of cold. It is a statistical departure from an average. a region where the temperature of photons that have been traveling for nearly 14 billion years is very slightly below the mean temperature of all the other photons that have been traveling for nearly 14 billion years. It is cold in the sense that a number is smaller than another number. Cold in the abstract language of physics rather than in the language of the body. And yet there is a way in which the cold spot's coldness carries weight. Not the weight of felt experience, not the shiver that runs through you when you step outside on a winter morning, but a different kind of weight. The weight of significance, the weight of anomaly, the weight of something that does not fit, that refuses to be explained, that sits in the data like a question that insists on being asked. The 70 microkelvin temperature deficit of the cold spot is, in absolute terms, tiny. But in the context of the CMB, where the entire range of temperature variation is only a few hundred microkelvin, it is large. It is the equivalent, in human terms, of walking into a room that is supposed to be uniformly heated and finding a corner that is significantly, measurably, noticeably cooler than everything else. Not a drafty corner, not a corner near a slightly open window, but a corner that is cold in a way that cannot be explained by anything you can see in the room. You would notice it. You would stand in the corner and feel the cold and try to understand where it was coming from. You would look for a source. You would look for an explanation. And if no explanation were forthcoming, if the cold persisted despite every investigation, if it was still there every time you checked, then eventually you would have to consider the possibility that the source of the cold was not in the room at all, that it was coming from somewhere else, from beyond the walls, from outside. This is, in the most metaphorical sense, the situation that cosmologists find themselves in with the cold spot. They have looked for the source of the cold inside the room of the standard model, and they have not found a fully satisfying answer. The foreground is not the source. The instruments are not the source. The statistics are not a fully comfortable explanation. And the super void, the closest thing to an inside-the-room explanation, falls short, which leaves the possibility that the source is outside the standard model, outside the single universe framework, outside everything that cosmology has so far been built to contain. The weight of the cold is the weight of that possibility. The weight of a question that may have an answer more extraordinary than any question in the history of science has ever had. Feel that weight now gently, not as a burden, not as something that should keep you from sleeping, but as the particular, rare, precious weight of a genuine mystery. A mystery that the universe has preserved in its oldest light for nearly 14 billion years, waiting for the moment when there would be minds capable of asking the right question. And here we are, capable of asking, beginning to understand, reaching carefully and honestly and without certainty toward an answer that may or may not be within our reach. The cold is there. It has always been there, and now you know it. The multiverse fingerprint is not just a poetic description. It is a scientific hypothesis with testable consequences, and the testing of those consequences is ongoing and will continue to be ongoing for as long as there are scientists interested in the question and instruments capable of addressing it. Future CMB experiments are planned that will measure the polarization of the ancient light with greater precision than has been achieved by any instrument so far. The polarization of the CMB, the way the electric field of the microwave photons is oriented, carries additional information about the conditions at the surface of last scattering and about the large-scale structure the photons have passed through on their way to us. A bubble universe collision would leave a specific polarization signature in the CMB, a pattern of polarization correlated with the temperature anomaly of the cold spot that would be difficult to produce by any other mechanism. If future instruments measure the polarization of the CMB in the direction of the cold spot and find that polarization pattern, the Bruise theory will be significantly strengthened. Not proven, not beyond all possible doubt, because science does not work in absolute proofs, but in degrees of evidence, but strengthened to a degree that would make alternative explanations much more difficult to maintain. Similarly, future galaxy surveys will map the large-scale structure of the universe in the direction of Eridanus with far greater precision and depth than the current surveys that revealed the supervoid. These surveys will tell us, more precisely than we currently know, how large and how deep and how distant the supervoid really is, and whether its properties are consistent with what a bubble universe collision would produce. The fingerprint is being studied. The science is ongoing. The question is being pursued with the patience and rigor and collective effort of a community of scientists who understand that the possible importance of the answer justifies the work. And somewhere in the future, perhaps in the lifetimes of people alive today, perhaps not, there may be a moment when the evidence is strong enough to say, with the kind of confidence that science reserves for its most established conclusions, that the cold spot is a cosmic bruise, that the multiverse is real, that our universe is one bubble in an eternal foam, and that we have found the fingerprint of a neighboring bubble in our oldest light. Or the evidence may point the other way. It may accumulate in a direction that makes the Bruise Theory untenable, that demonstrates that the cold spot has a more ordinary explanation, that the multiverse, whatever its theoretical appeal, has not left the kind of mark in our universe that we have been hoping to find. Either way, the science will have done its job. It will have taken the question as far as the evidence allows, followed the data honestly wherever it leads, and arrived at the best possible understanding given the limits of what we can observe. That is all science can ever do. And it is, when you think about it, an extraordinary thing that it can do even that. The fingerprint is there, or it is not. The bruise is real, or it is not. The multiverse is our context, or it is not. And the honest, patient, ongoing work of finding out is one of the most remarkable things that any species has ever done. The cold spot is there. The ancient light is everywhere. And the question, vast and patient and unresolved, is still alive in the sky above you tonight. Rest now. Sleep. The universe will keep its secrets a little longer, and so will you.